exciting day in Stat 201.
Jason, no. Jason, no. Out of the shot. Jason. Mark, where is everyone? Why is everyone in the shot? This is Stat 201. No, Jason. Jason, no. That's perfect, Jason. Leave it right there. No, Jason. What? No. Jason, you're out of the shot. Jason, no. Hey, Jason. No. Why aren't you behind the camera?
And now, Stat 201.
Hey everybody, how are we doing? That's a throwback intro with Jason right there and Mark, if you know Mark Collins and Jason Greenway. People, you might know Mark Collins. Jason Greenway, though. Can everyone hear him and see me? Who's the group in the background? Do you know Mark Collins? Mark Collins is great. And a huge thank you to them because we're really lucky because, you know, what we can do right now with the class, being able to teach online, being able to do all this. I think everyone can hear and see me. I'm always checking that and help me do. There we go, the volume. For some reason, I don't know, I think it was when I updated the computer, and I will say this, if Dennis is watching, the computer's working at 100% right now. I updated the computer, put all the Windows updates, and the memory usage and everything is really awesome. And for some reason, though, it changed like the microphone or whatever, and so when I go to Texas, I'm going to reset everything up. But we got everything working again yesterday, because I remember yesterday when I started, and everyone's like, we can't hear you, and I'm like, oh no. Is it super proliferate? And Emily, go down to the bottom, go down to oh, I can't go in front of this. Go down, yeah, Windows updates are finicky. And go down right here, Emily, and see if it's running. You'll see a little scroll wheelie thingy. Let me do this. Let me do this. Yeah, I think it like had some problem with the Go XLR, like the Windows update drivers and stuff. So if it is blurry, I should make a video on these things. Extra credit. If it is blurry, you should see a scroll wheel button right about here. Am I blocking it? Boop. And so there's a scroll wheel. That's a scroll wheel if you can't tell. And click that scroll wheel button below right there. And you should see if that fixes it, Emily. Then you should go to like higher. A little further to the right. All right. Oh no. Well, I've done it. Okay, wait. Is it right over? Is it over here? Oh my gosh. All right. Wait. So it's like right about there. You see it? Did that fix it? Awesome. Okay, let's hop back to right. Let me put myself back on the screen here. Perfect. There we go. Yep. And yep, awesome. Well, I'm glad. That's it's just yeah. Awesome. Thank you everyone so much. It's been an amazing summer and you guys really make the class. And Dennis, thank you again for the Discord and everything, which we're going to be working on. Like you've got the ball rolling on it. And thank you to Alex especially and Brad. Alex, Dennis, and Brad have been really big on the Discord. So hop into the Discord if you haven't yet. Once again, one last big promotion on it right here. But I'll be focusing on it a lot. Probably be talking to Dennis a lot and all that great stuff. How's everyone doing this morning? How is everyone doing? Let's see here. Let's get some info from everybody. How is everybody doing? I am like, I can't believe it. I can't believe today is our pretty much the last day of new material. Good. Hey, ready for the week? I know. Is anyone else starting another class? Because next class would start on Monday, right? So you get the weekend off. Some people have told me that some people have said they're taking 3 classes this summer, and I'm like, oh my gosh, that is insanity. Like, or like 4, like some people are taking 3 classes right now, and good job if you are. That's a lot of work. So, a lot of work. But it is time to finish up logistic. Now, one thing I want to point out, because these are some huge things. Yep, we're doing a Kahoot tomorrow, probably about 3 or 4. It'll be like during office hours time. I'll go over a lot of material. And so it'll be, I wouldn't take the test right away. Oh, you're welcome. Oh, thank you, Connor. Thank you, Connor. No, you guys, you know, I really appreciate it. And it's, you know, you guys make the class. Like it's, if you guys can't tell, like the days we have the most energy is like you guys fill me with the energy. You guys like, we bring the energy here for each other. I bring you the morning energy and we bring it right back. So we're ready to go. It's 8 a.m. We got this. I already drank my Red Bull. I would take the sip of the Red Bull, but I'm trying not to have 2 in the morning, just 1. Well, thank you, Emily. Thank you guys so much. You guys have been working really hard and we're all working together and always be asking questions, always be following along. That's the best we can do. And that I really appreciate it because you guys have been amazing. And I don't say that lightly. It's like, man, it's, it's crazy times, but you guys have been there and we've been working hard. So with that, let's talk about some logistic regression. With logistic regression, the number one thing, we started yesterday's class with this. I'm gonna give someone 1,000 points. We're just going crazy. I know I'm like destroying the point system, but I don't care. It's points. With logistic regression, the number one thing you instantaneously need to know is this. Like, you have to know this about logistic. It has to be the first thing on your head whenever you hear logistic. You're like, oh, that's a thing. That's a that. Like, the first thing you hear when you hear logistic, you instantaneously have to know this difference. Boom, Mila right there got it. She knows instantaneously it's a categorical Y. And I'm going to throw it to Brad also. Brad also knows GLM. And Brad gets 1,000 too, because that's the thing you need to know instantaneously. Because when I hear GLM, I'll give Megan points right there, 1,000, predicts a categorical Y. Boom, Nicole, 1,000 also. You got to know these things. And Emily, we'll do 2 more. Who else knows this? This is your wake-up call right here. Wake up in the morning. You have to know this. If you can't tell how much I'm stressing this, it's like the whole point of the chapter. The whole point of the chapter is that logistic is going to predict a categorical Y. Connor right there also. You got it, Connor. And Emily. There we go. So with this right here, and Sylvia, it's everybody's wake-up call. And James, anyone else? Alexa, yes. Nicholas, Stevenson, exactly. Now, watch this. 5,000 points, crazy points. What is the other extra argument we have to add in there? He'll be typing it out while I've got it on the screen. You have to know this. I'm dropping some hints for the take-home. I am dropping hints for the take-home. There's some tough questions on the take-home. There's bonus on the take-home. Boom, Brad right there. Brad was quick right there. Everyone else gets 1,000. Brad gets 5,000. Brad was quick. Brad was ready to go. He was like, I know what the next one's going to be. Brad's like, I got this. Great job, Brad, right there. So amazing work. And it's really fun to see who has the most points. Like, I really like looking through that. You can see if Streamlabs is awake. Streamlabs is probably awake. So, okay. Hopefully everyone's following along and understanding what we're talking about. We literally just in the 3 minutes mentioned some things that you have to know instantaneously right here. You have to know that churn is a categorical variable, and you have to know that we're using the function GLM instead of LM, and you have to do family equals binomial. You have to do these things. That's key for the take-home. I'm trying to drop some hints here. I'm like not saying how to do the take-home, but I'm just saying that you need to do family equals binomial and GLM. GLM stands for generalized linear model instead of doing a linear model. So that's all that's going on right here. This is where we ended yesterday, and we were talking about how to interpret coefficients. Some key things we need to see right here. Let's see here, 1,000 points each. We'll just do first person right now. We have, with the number of calls here, comparing 2 otherwise identical individuals. Why are we saying otherwise identical customers? Why do we have to add in this phrase of otherwise identical? Why am I saying like, this implies that 2 otherwise identical customers? Why are we doing that? Why do we have to add in this phrase? I'm not going to lament the fact that we're not doing written tests again. I don't want to, I know, like, I'm going to look at the answers when it's all right. Please tell me if you think there's an error. We did find an error on the midterm, and I had to regrade some midterm stuff because it's a multiple regression. Brad's right there. Brad's right, it's a multiple regression, and you have to remember in multiple regression, you have to say between 2 otherwise identical individuals. And so in multiple regression, you have to do otherwise identical individuals. You can't just say 2 individuals who differ in this amount. James is right there. Multiple regression. When it's multiple regression, you have to say otherwise identical. You don't have to do that for simple linear. When you compare 2 individuals who have 1 month difference in their last month since gift, you can just say that 2 individuals who differ in their last month since gift by 1 month are expected, where one individual has given more recently. The individual, well, see, this is longer. Let me reverse it. 2 individuals who differ in their months since last gift by 1 month. The individual who has had a longer time since last gift is more likely to not donate. You can see the coefficient and you can see the curve going up. And the probability is the probability of no, because the other one is donate. The level is donate no, and that is logistic last. Review from yesterday also. Logistic, the level of interest is last, meaning that the level of interest, the thing we were predicting, is the last. You might say, well, wouldn't that be yes? Well, it's because this variable has donate and no. So the levels are donate and no. The levels are not yes and no. So that's confusing because you would think it's yes and no, but it's coded as donate and no. So, yep. And it says right here, there we go. the levels are donate and no. And in logistic, the level of interest is last. Okay. And so please ask questions if you haven't. This is like a mega review. We're literally doing a mega review right now. If it's all making sense, awesome. If it's not, slow me down. And so we get right here where we see the two individuals who are otherwise identical, multiple regression interpretation, where they differ in their number of calls to customer service by one call. The person who calls customer service more. Now, what do we do in logistic? What do we do with this number? Okay, wait. Okay, wait. I'm going to say two interpretations and don't answer yet. We're going to do a poll in the audience. You're going to tell me if it's the answer is A or B. So let me get the poll going. I'm going to give you two interpretations because I'm already getting test questions up and going. And I want to see which one everyone votes. Will this hurt Brian's heart or will it not? Okay, so we got the poll. Don't vote in the poll yet because you'll see A and B answers. Don't vote in the poll yet. Okay, I'm going to start the poll. Don't vote because I haven't said what the answers are. Poll is going. Okay. So with the poll going, you're going to vote A or B. Here we go. I'm going to interpret the coefficient twice, and you have to tell me which one's right. Two individuals who are otherwise identical, who differ in their calls to customer service by one call, the person who calls more is more likely to churn. Interpretation A. That is interpretation A. Two individuals who differ in their calls to customer service but are otherwise identical, where one individual calls customer service more, the person who calls customer service more is more likely to churn. Interpretation A. Two individuals, interpretation B. Two individuals who are otherwise identical, who differ in their calls to customer service by one, the individual who calls customer service more is 51.8% more likely to churn. Two individuals, interpretation B. Two individuals who differ in their calls to customer service by one, but are otherwise identical, are expected to differ in their churn rate by 51.8%. Interpretation B. Which of those was right? Interpretation A or interpretation B? Let's see what people say. No, I can't trick you guys. Good job. It's all right. If someone votes B, it's all right. Someone's like, I'm going to go against this. I'm going to go against. Brian's already kind of admitted it. He's like, I can't trick you. But am I tricking you by saying I can't trick you? The answer is no. You're right. 100%. Great job. Sorry, everyone was doing it. Sorry for everyone. Don't worry. The votes don't track. I really wish I could do betting. Start bet. See. Oh, you see, betting's weird. You have to do there's a way it works. I just don't think it works. It just doesn't work on YouTube, and I have no idea. If you want to bet true, you'll get points, but I don't think it. We tried it. This is our last try on betting. Maybe they've updated it. We've seen the Streamlab icon update, but we also don't know people's points beforehand. So don't vote false, whatever you do. If you want to try to bet, vote. Yeah, and there it is. Ryan's doing it properly right there, and it should show up Ryan's bet. So the interpretations you heard me, is people try to bet because I'll just award true the winners. And Ryan and everyone, take a look at your points right now and then take a look at it after. So if you've already bet true and you bet 100, take a look at your points. And so people start checking your points. And then after I award the money, check the points again, the money. I'm not betting real money. So take a look at your thing. And this one's a bet one because I really wish we could do betting. Whoa, that'd be so cool. I mean, that makes it even funner when we do these if we do betting. So, okay, well, let Streamlab do its thing. Remember when Streamlab was double reporting? It was weird. Okay, so with this in mind right here, do not interpret the coefficient. What I've highlighted right here, do not mention this coefficient. Because look at these. What is this? Negative 21%? No, it's just a very negative coefficient that total day charges, two people who differ in their total day charges by 1 unit, whatever that is, the person with more total day charges is less likely to churn, probably because they're using their phone more often. It's also not statistically significant, so I wonder how that's collected. So we've done it. We've got the bets. Let me close the betting. Let me pick the winner. Winner's been picked. Okay, wait to check. It's going to say true was winning option with 100% of the bets. Good thing you didn't bet false. And so now go ahead and check your points again. We'll see if it awarded the points. Loyalty points. Ooh, it might have worked. Unless it's the way I set it up. Oh, wait, complete. Okay, wait. Okay, try options. Who's going to win? Advanced. Minimum, maximum duration. Okay, wait. Okay, we're going to try this one more time. This is our last thing. Okay, we're doing a 20-second bet. And bet true again. No, we'll do 60 seconds. Bet true again. You can bet up to 1,000 points. So I'd probably bet 1,000 points RU. So there's probably 3,000 points. Oh, I shouldn't do that multiplier then. Okay, I think I might have found the issue. Send chat notification. Good. Okay. We're going to give one more try at this. It's going to win. Free points are good. True is T, and false is F. Okay, we're going to give this one more try. Did Brian finally figure out betting on the last day? Okay, so the betting has started on free points are good. So give this a shot right here. Free points are good. Bet true and bet the 100 points after. And so let's see. I don't think, let me see, did Ryan? Okay, good. And we'll see what this does right here. This is my bonus on the second to last day, because I might have just figured it out. Okay. Oh, wait a minute. Do you see? It's never said that before, has it? Oh. I think we've done it. Oh my gosh. Wow. Okay, so you've only got like 3 seconds left on this. It's our fun for the morning. And so, are you ready? Time. Let's close the betting. Let's pick the winner. And then let's complete the poll. And let's see if it did it. Okay, so now, let's do this. I think it worked. Because it's literally saying they bet it. So Dennis is looking at Dennis's points. You guys tell me if it worked now. Oh, everyone's excited. I love the interaction right here. I love everyone being like, oh, let me look at this. We might have done it. You guys tell me in the chat if it worked. Oh, it didn't. I know Dennis had around there. Okay. Streamlabs. Get your act together. I know, right, Dennis? Dennis, we need to figure this out. Okay. Here we see more interpretations. Sorry. It did something. I set up everything as I could. So what we need to do is we need to talk about just a few more topics today. We're having a little bit of fun. It worked the first time? Oh my gosh. Well, I don't know. I'm going to figure this out. Sorry. Hopefully people understand the only way for me to test these things out is to be on a live stream with people. And so that's where I do the testing of it. And one of these days you might just see me like a YouTube video titled like testing out Streamlabs. And I'll be like on there just like doing things. But I have to be live. I can't have a private video. YouTube has to be on a public video. If it's on a private video, Streamlabs doesn't work for some reason. But it's not programmed to work that way. And if I was on Twitch, it has way more features. I can do way more on Twitch with Streamlabs. It's more integrated to Twitch than it is to YouTube's API or whatever it is. It just doesn't grab the information as well from YouTube. So they don't like YouTube as much. And they really don't like Mixer. Haha, sorry, Mixer. Sorry, I'm kidding. Sorry, Ninja. Well, he made a lot of money. Ninja's fine. He's fine. Ninja's doing well. Okay. So in multiple regression, let's look at this right here. We have interactions. In multiple regression, we have interactions. And this is one of the biggest things right here. So here we are with our variables x1 and x2. If you notice right here, this is implicit lines. We have here x1, we have here x2, and there's no interaction on this. It's just b0 plus b1. Now, what is b1 in this model? What is b1 in this model? Ooh, that's a decent question. Just think, Alex, you're like our king of questions. Like, I like seeing the screenshots of like, you know, like, what is b1? And that's like, what is b1 in this model? 1,000 Boys who knows what b1 is. What is b1 in this model? What is B1 in this model? Don't be tricked, because I almost thought it was something else. And I was like, oh, it's actually that. What is B1 in this model? Yep, Mila, great job. 1,000 points, you're right. Yep, it's -1. because there's a 1 before something if it doesn't have anything. It's -1. Exactly. So that is -1 right there, and B2 is -2, and there's X2 and X1 and B0. So it's important to know that this is the format B0 minus, well, I mean, it's a minus B1 X1 minus B2 X2, and so B1 is -1. And so in logistic, it's going to look a little bit different. In logistic, as we draw these what are called implicit lines or implicit curves, implicit lines, implicit curves, we are saying like we are literally going to solve this. And here's what's the confusing thing. And hopefully for people who've been working on the assignment, this makes sense. If you were to add a constant, to a linear model, like if you were to solve this out and just put in a value here for x2, and you were to add a constant, 1,000-point question, what would this change? If you were to make this a constant and add it to this, what would it change about this part over here? If you were to put in a constant right here, and I'm going to like mark it like 3 times, so I can't highlight it again, I really wanted to. If you were to turn this into a constant and add it, what would it change about the model? If you were to make this a constant and add it to this, what would it change? Make this a constant. The intercept, Mila, amazing. 1,000 words again. Mila, keep it up. It would change the intercept, and you can see that right here visually. Does that make sense? That if this were just become like 2, it would change that. If it were to become 5, it would change this. And by plugging in values of x2, you're going to change the intercept. Like, just don't even think that this exists, and just think of it as simple linear regression, and you would be changing the intercept by putting a constant in and changing this right here. It'll change that value because this will become like 2, and that's 2 times 2, it's 4. This will become -2, and it would decrease the intercept down. The intercept would go down. So we can see what happens right here as we put in different values. Like if we put in 2, then the line would go down to here and be changing the intercept. Now you'd say, wait a minute, this is not changing the intercept. But does everyone remember from yesterday, the intercept controls the 50-50 breakpoint. The intercept in logistic, the ratio of negative B1 over B0. Let me double check that. I'm always afraid when I say that one off the top of my head. It should be the ratio of negative B1 over B0. And where is it in the slides? Negative B0. I knew I got it wrong. I knew I was saying it wrong. I was like trying to think through it theoretically in my head. It's negative B0 over B1 is the 50-50 breakpoint, and that's related to the intercept. So that's not the intercept, but the intercept can be used for it. Does that make sense to everybody? Theoretically, like this is the value of the intercept, and then we divide it by the slope to look at the ratio of the intercept to the slope, and then we get right here where it changes from 50-50, like where it goes, we would predict yes, and we would predict no, or this one's predicting live. But if we're predicting yes or no, it's predict yes. And a lot of logistic is predicting yes or no. Like a lot of logistic questions are set up to predict yes or no. Because a lot of times we're interested, like, will somebody buy this product? And then the probability of yes. Will somebody die? The probability of yes. Will somebody churn? The probability of someone's churn, but churn yes. So what we have right here is this is basically the intercept. It's not the intercept, but it's found from the intercept. So this point right here, if we change the intercept, this point will do what? Just show you're following along. What will that point do if we have a different intercept? If the value of the intercept were to change, what would happen to this also? Because the slope's not going to change. If the value of the intercept were to change, because the slope controls this. So the lines would still be parallel, but it's just going to move where this is at. Because think, the slope controls the shape of it. Does that make sense? Like the slope is like this of the line, which that didn't change for the linear. Remember the linear models were all like this? They all had the same slope. And so these are all going to have the same sigmoidal shape, i.e. same slope, but they'll have different intercepts. Who's following me with this right here? Like in linear regression, if you just change the intercept, it looks like this. So it would stay on a y of 0.5, but the slope would change horizontally. Brad, expand further. So the sigmoidal shape, the 50% intercept would move left and right. Exactly, Mila. It would, this right here, this is the ratio of the negative intercept to the slope. And since we're changing the intercept, since the intercept is changing, it's just going to move where this point is at. Because the slope, which is this, now we don't just that's the slope number. The slope controls the sigmoidal shape. And so we've got the vertical set to yes. Yes, exactly. This right here would change. And so this would change right here, the vertical line. Exactly. So you'd move this like over, and that would move the curve over to the left or to the right. And you can see that visually happening right here. So this is where Brad was saying you would move this point over like this, or you'd move it over like this. Now the slope is still the same. The slope has not changed. The sigmoidal shape of it has not changed, just like the slope of these lines has not changed. The slope is not changing, the intercept's changing. The slope is not changing, the intercept is changing. And the intercept controls the 50-50 breakpoint. So you can see it's just moving it left and right. And so that's one of the tricky things about logistic is that you have to remember this is not a line, it's a sigmoidal curve. And so we're fitting this curve that has an intercept that is going to control the 50-50 breakpoint. And you can see right here that there's a different 50-50 breakpoint, but the slope is going to remain constant. We're plugging in values of x2, so the slope of x1, which is right here, is going to remain constant for this curve. Statistical significance. Now I'm going to talk some big stuff here, especially for the take-home, so get ready. So there's some hints being dropped for the take-home here. I'm going to try to drop as many hints as I can. There's some really tough bonus on the take-home. Remember that I think it's questions, this is off the top of my head, I think it's 8, 9, and 11 are bonus on the take-home. If those are too tough, don't do them. They're pretty tough take-home bonuses. A lot of them, they deal with things we have not covered, but I left them on there for people who want to do bonus. If you can't do them, don't worry. Don't spend 5 years doing them. You don't have 5 years. So they're on there if you want to do them and take a peek into other things we do in statistics and business analytics. But don't do them if you're like, I can't do these. I've spent too much time. Focus in on the other ones because they're worth the big points. So when it comes to statistical significance, this is the thing that just blows my mind. So with this being bonuses, does that change the 35 points for the take home, or does that just make each question's worth more? Yep. And so each question is worth more. So focus in on the big ones. Would you say it the same of the bonus side? Yeah, I would say that too. I would, if I was everyone, I would only, at this point, especially with how little time we have left, if you did the bonus like this weekend, if you're caught up, I would not try to be like, I'm going to, spend all day tomorrow doing the bonus. I'd be studying for the final. Like the bonus has been there, just depending on how much time you have. Like there's a lot. It's like I would spend making sure I get the take home done, the last homework done, and I'd make sure I'd like take home, homework, study for final. And then the bonuses are the extras on that. They're worth way less. Like take home's huge, study for final is huge, last assignment. I'd probably do it in that order. I'd do take home, study for final, last assignment. But if you already have if you have homework grades that have been dropped and you can't afford another bad homework grade, I would do the last homework a lot more too. So my order once again is take home, because you don't want to not turn that in. Study for final, because you can take the final without studying. I would still study for it. And then I would do the homework. So, but don't not do the homework. So you might be wondering why I'm going backwards, because I'm going to show you one of the paradoxical things right here. Here's what's paradoxical. Things that you wouldn't believe. How statistically significant is this variable on a scale of like not significant to super significant? How significant is this variable on a scale of not significant to super significant? How significant is this variable on a scale of not to super? It would be worth, I believe so. Yep, Dennis, I believe that's correct with the syllabus. I'm 99% certain. Oh, wait, it's not significant? Wait. Can I type it into the calculator? How significant is that variable? It doesn't even show it to me. Very. Yeah, I know, right? And so I can't even, it's off the screen, everything. It's super significant. But here's the confusing thing. You ready for this? When you look at this model down here, here's the 50% line. This model predicts that everyone will what? The model predicts that everybody will what? The model predicts that every single person, no matter their months since last gift, will what? Like you could have someone down here who has like 4 months or 10 months or even 0 technically. Like I could solve this out for you. There's a quick solve for it, I know. But even with 0, the probability would be above 50%, would not donate. And so every single person, no matter their months, would not donate. And you can see that this is actually the sigmoidal curve if you were to zoom out on it. So even at 0, which if I put the line well enough, you'll see that even at 0, it's above 50%. And I can promise you that because the quick solve also solves it that way. And so even at 0, we're above 50%. You'd have to have negative months for us to predict you would donate yes. Because here's donate no above the line. Oh, and that's where 0 is at apparently. That's not 0. That's maybe 1, or I don't know why we have the line there. But as you can see, oh, that's where the window was. That was the window we saw. This is the window of that, and that's the window of that. So this is the sigmoidal curve, and it is super significant, but it does just as bad as the naive model. And this is where we talk about statistical significance and what it means. What we're looking at is the deviance from the model, and this will be the statistical significance. You don't have to know too much about this. It's just that you can have something in a logistic model. This is the big thing. You can have something in a logistic model that is super significant that doesn't help at all. You can have something in a logistic model that is super significant that doesn't help at all. And that's the weird thing. That's the super weird thing about this. And so when we talk about this, we're talking about how much it deviates from the naive model. And once again, when we use the naive model, what would the naive model predict for the model where most people do not donate? If most people do not donate, what would the naive model predict for everybody? You guys might be saying it in the chat, or I think I asked the same the answer because it's already there. If most people do not donate, the naive model predicts the what? If you see things underlined, they're huge. If most people do not donate, the naive model will predict this. It will predict that nobody donates. It's kind of like saying this. You go down to UT campus, and you go down on game day, and you go to tailgate. Do you think that tailgate is going to be in favor of UT winning or against UT winning? You go down to UT campus on a game day, and you walk up to a tailgate. Do you think that tailgate's going to be in favor of UT winning or against UT winning? Favor or against? What do you think? You walk up to a random tailgate on game day. Do you think they're going to be for UT winning or against? For. Exactly. And you might say, well, but there's people there who don't want UT to win. You're like, well, yeah, but you just go with the majority. Because when you make these predictions right here in logistic, the naive model starts out with the majority as the naive model. Sorry, guys. The naive model starts out with the majority as the naive level, or the naive model starts out with the majority level as the naive model. And so with this right here, if most people on game day tailgating, if most people on UT's campus tailgating on game day would want, I got this. If most people on, I think I'm going to grab some water real quick. Okay, now I'm all right. Just say I'm going to grab water and fixes everything. The brain knows to fix it. So let me repeat that. If most people on campus tailgating on game day want UT to win, you would just say everyone on campus on game day would want people to win. But let's think of some variables. I need your guys' help with this. What would be some predictors in the model that would change the deviance? So we're going to try to kind of change it and add statistically significant. What could we collect on about these individuals? Like, what could we collect on? I think there's a really easy one. I don't want to steal the answers, though. I don't want to steal the answers. What could we collect on? What predictors? Color of clothing. That's exactly it. That's exactly it. Are they wearing orange? We can say, are they wearing orange? That's a pretty big, like if they're wearing orange, I would think that would definitely change the probabilities. What else could we collect on? Anything else? Maybe, have they ever been to UT before? Because you could be like, some people who have been to UT before would be, because you might say, well, maybe it's the Florida game, and maybe they come every Florida game. Maybe they're, new to Knoxville. maybe they're, they're still from UT, or maybe they're, like their family invited them down. Who knows? But I think there'd be a trend that people who have been to UT more and are wearing orange would be more likely to be fans of UT, like want UT to win. That there's a relationship, a statistically significant relationship between how many times you've been to UT, and also what color of clothing you're wearing, and whether or not you want UT to win. If you just imagine someone being like, "Whoa, this is my 10th game," and they're wearing orange, and you're like, "Yeah, you're a big UT fan, right?" They're like, "Oh my gosh, yeah," and you'd be like, "Well, obviously." Our brains kind of know how these models work, and I don't think people understand. We are doing these statistical models in our heads. We do statistical models. We make predictions all the time. You see someone, what is it? Auburn wears red. So you see someone wearing red. Oh, you see, but we even do interactions, because during the Florida game, what interaction is there with color? What color interaction is there? Because you could say red is Alabama. I'm so bad. I don't know colors. What interaction is there with orange during Florida games? Like, you could say someone wearing orange increases the probability unless this. What interaction, if I am correct and know my colors for teams, what interaction is there with the Florida with orange? Or my thing is something totally different. You guys gotta help me out, because if I'm thinking of, it depends on home or away, right? What interaction is there with Florida and orange? I might just say it, because maybe I'm way off and you guys will have to correct me. Orange and blue or orange and gray. Yeah, exactly. That is right, because Florida's orange and blue, right? So if someone's wearing orange and blue, then orange, it like counteracts it. Yeah, exactly. Blue and orange. So that's what I thought. Because now you've just done the interaction. Because you would say somebody is more likely to want UT to, exactly, they got an ugly orange. Is it good orange or bad orange? Someone is more likely to want UT to win if they're wearing orange. But if they're wearing orange and blue, then you automatically just, the problem, like, it totally, does that make sense what the interaction is? Like, wearing orange, the way you're wearing orange depends on the color of the orange, and also what supplemental color you're wearing with the orange, like what secondary color. Like, orange does not always increase the probability of someone being a UT fan. That's an interaction. You've literally just done an interaction in your brain. You understand that the way in which somebody wears orange, the color of the orange they wear, will control the way in which they want UT to win. Because if you walk up to someone, you're like, "Oh, if they're wearing orange, they'll want UT to win." You walk up with someone with orange and blue, you're like, "Yeah, UT's the best, right?" And they're like, "What the world?" TN orange, every other orange. I like it right there. So I like talking about how we actually do statistical models in our head, like how we're actually changing the probabilities, and we understand these things. It's just weird when we put math to it. Like, when we put math to it, you're like, "Wait a minute, we can solve this mathematically." And it's like, yeah, we can do it mathematically. We already do it in our brains, so let's do it mathematically. If it's not PMS 151C, it's garbage. I think it's FF 1900. The RGB color. I could look it up in the back right here. I should know the RGB color. I put it in a lot. Dennis, you might help me out on that, or someone. That's the Pantone color. I think it's FF 1900 for RGB colors. And here we are, FF 82. I should remember that. That's why. It's my birth year, because I was thinking it did something with my birth year. It's FF, my birth year, and then 00. So it's a bunch of red, a little bit of green, no blue. No blue. There is no blue in our orange, because that last one is RGB. If you're wondering how it works, that's hexadecimal color coding. And it works on, there are 16 possibilities with every combination. So since it's hexadecimal, there's 256 colors of red you can put in, 256 colors of green, 256 colors of blue, based on numbers 0 through F. It's pretty cool, hexadecimal color coding. So you can look at it and you can be like, okay, it's the highest amount of red, it's all red, it's a good amount of green, and then it's no blue. And the weird thing about hexadecimal is that when you count in hexadecimal, you would count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then what comes after 9? What comes after 9? If you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, what is the next number after 9 in hexadecimal color coding? Or, yeah, it's A. Yep. You go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. That's hexadecimal. And so the highest number is what in hexadecimal color coding. Because 99 is actually not that big with hexadecimal. In hexadecimal, the highest number would be, I think Brad gets it right here. It's in the color code right there. So that is the highest number of, yep, it's FF. So you can think of it as FF8200, and that's the amount of red, that's the amount of green, and that's the amount of blue. There's no blue, there's a medium amount of green, and then red has the absolute highest amount of red. And so there you go, something random you learned right there. And so with this right here, we can see that we're predicting diabetes, and we're using if somebody was pregnant, which means, yeah, it's pretty useful. It's just more you know how coding works and everything. And once you understand, it's like, okay, it's just 16 numbers. That's all it is. And FF is the biggest 2-digit 16 number, which is basically like 256 in standard mathematics. So with this right here, we see that someone being pregnant adds additional information that the other variables are not, well, it's just one variable. So someone being pregnant explains, like changes the deviance of the curve, but we do not know whether or not it actually changes the model, but it changes the deviance of the curve. And what do I mean by that? It's going to make the slope different, but as we saw previously, it might not actually change the slope in a way that would actually change the way we do predictions. We can see that right here, where it's not changing the predictions. So it just changes the deviation of the curve. And so down here, pregnant now is not going to change it. It also does not add significant information to the model. What really adds significant information to the model is glucose. In this multiple regression, we want to see whether or not it's changing the deviance of the model. And don't worry, I won't focus on that too much, but it still follows the thing that glucose adds significant information to the model with the other variables already in the model. Pregnant had significant information, but now it no longer has it. So in multiple regression, we always stress the point of it's what do you bring to the model with the variables already in the model. Pregnant had information about diabetes, but it no longer does. It means it brings the most significant information. Like to talk about what glucose does right here is with all the other variables in the model. That's one of the key things. With all the other variables in the model, glucose brings with it the most new information that the other variables are not accounting for. With all the other variables in the model, glucose brings with it the most new information that the other variables are not accounting for that changes the deviance of the model the most. What do I mean by changing deviance? I mean like changing from the naive. Like here's a flat naive and here's a change in deviance. It doesn't mean it's actually going to make better predictions. It just means that glucose is the variable that brings with it the most new significant information that the other variables are not accounting for because it's multiple regression, and thus it would change the deviance of the model the most away from kind of the naive model. Does that make sense, Alex? Whereas pregnant had significant information, but in the multiple world, it does not bring with it new information. Like there's probably an overlap in the information pregnant brings with the other variables. Like being pregnant would be correlated with your age and I don't know, blood pressure. But I do not know that for a fact. Age would probably be some way correlated or connected to pregnant because there's probably ages people are more likely to get pregnant. So, I mean, yeah. So p-value is what tells you what has the most in these new information, what gives you this, not so much strength. I mean, a little bit of strength, but more new information. In a multiple regression, the p-value is associated with the variable bringing with it new information. So you can't say that pregnant has nothing to do with diabetes. Pregnant in this multiple model does not bring with it new information. Being pregnant is connected or has an association with having diabetes. Like being pregnant and like the amount of times you're pregnant, because that's not pregnant, yes, no, it's amount of time you're pregnant, because it would have an indicator if it was yes, no pregnant. The amount of time you're pregnant does have an association with whether or not you have diabetes. But in the multiple model, it does not bring with it new information that the other variables are not accounting for. It's not statistically significant. So it is significant by itself, but in the multiple world, it does not bring with it new information that the other variables are not accounting for. This is key and why I've paused on this slide, because this is big for all multiple regressions. If you see a variable that is significant in a multiple regression, it is not bringing with it new information that the other variables are not accounting for. Now, does this mean glucose by itself is significant? Is glucose in this model right here, does this mean glucose is significant by itself? Yes or no? Yes or no? Does that mean glucose is significant by itself in the multiple, because we see it significant in a multiple model? The answer is most definitely what? Correct. It's no. Because right now we know that glucose brings with it new information that the other variables are not accounting for in the multiple model. And it changes the deviance in the multiple model. We do not know about the simple world. So whatever happens in the simple world doesn't have to happen in the multiple world. Like pregnant was, glucose is going to be significant in the simple world, but I say that it'll probably be significant. But the way to find out is to run the simple model. So the way to find out if glucose is significant is to run the simple model and investigate just the one variable model. Like you don't want to say, oh, it's significant in the multiple. Well, then you have to look at the simple to see if it's significant by itself. And we see this right here. This means it's adding to the model with the other predictors, does not reduce the deviance. So don't worry. That's just kind of like changing from the naive again, reducing the deviance, changing it right there. And this means it's not adding in new information, doesn't help with the predictive power. So once again, we're seeing what does it do in the multiple world. By itself, it's really significant. By with the other variables, it is not. There are times when pregnant does not contain information about the probability of having diabetes. However, it looks that the information is redundant. And that's why something is often not significant in the multiple world, is that it brings with it redundant information. If it brings with it redundant information like pregnant has apparently done, that means its information is not new. If it brings with it significant information, it'll have new information. So glucose brings with it new information that was not redundant. Pregnant, we see right here, it was significant. And thus, in the multiple world, it has to have brought with it redundant information to not be significant. So what is the opposite of new information? Redundant information. If you have information in the multiple world, either your information will be redundant or new. If it's new, you're more significant. If it's redundant, you're less significant. Does that make perfect sense to everybody about, we're talking about like what this variable brings. And when you go to the multiple world, you have to say, is it bringing with it new or redundant information? And something we have not talked about in a while, 10,000 points. Redundant information will show up in the what's. Well, it's just such a good test question right there. And I wish it was just a written, because I hate doing written answers on the Respondus because they're so hard to do. Not the residuals so much. It's a really tough question. We haven't talked about this in forever. That's why it's a 10,000 pointer. Because we haven't talked about this in a long time. I don't know if anyone will get it. Redundant information will show up. I'm going to give it like 5 more seconds. See if anyone gets it. Redundant, kind of yes. Brad might. I'm going to give it to Brad because it could show up in that. That is technically possible for it to show up in that. That is technically correct. So Brad's got it. I could use the F-test to see redundant information. That is possible because you would not see a reduction in the sums of squared error. And so, but I was looking for VIFs or multi-collinearity. It would show up in the VIFs, the variance inflation factor, or multi-collinearity, which is a measure of the overlap between how our x's explain our x's. So those are terms that are on the final. We'll be doing a review tomorrow. But variance inflation factor or multi-collinearity would look at the overlap of the x's and how the x's explain the x's. If you remember, the variance inflation factor is 1 over 1 minus r squared sub I, sub e r sub I squared. And this right here would look at how the x's explain the x's. That's something way back. Philip, 1,000 points right there. Philip, great job. Redundant information will show up in the VIFs and multi-collinearity. Variance inflation factor looks at how much more uncertainty you have, variance is standard error squared, based on the redundant information in your x's, how your x's explain your x's. You don't want your x's to explain your x's. That's a bad thing. We're up to our last 2 things right here. And the last one's so easy. I would say this is the last hard thing for us to understand. This is the last thing. Get ready. Here we go. Then we'll do some review today also. And we'll do a review tomorrow. So we got lots of review ready for you. When it comes to interactions, we have to remember the way in which somebody's salary is explained by experience would depend on their education. And so we can highlight this right here. So let's do this. You can say the way in which experience explains salary depends on education, or the way in which education explains salary depends on experience, because it's not going to be constant. What's going to go on right here is that we don't have a constant coefficient for these because we have this multiplication term right here. So what did this change about the linear model? What did this change about the linear model? It changed, oh darn, we don't get to see it. What did this change about the linear model? What does an interaction change about the linear model? Hint, it doesn't change this. And I'm trying to change it off the screen just barely. It doesn't change this. What does the interaction change? The slope, meal 1,000 points again, you're right. It would change the slope of the line. So if you look, it's going to change the coefficient of the other one because it's like the coefficient of education, how it explains salary, depends on experience. So we would change the coefficient of one of these variables right here. So what's this going to change about the logistic model? Well, I'm just saying what's going to change right here. It's going to change the sigmoidal shape. So when x2 is either more negative or more positive, when is the relationship the strongest? When is the relationship here the strongest? When it is more negative, which is the very, very thinly dotted line, or it is more positive, which is this line right here. Here's the more positive line, and here's the more negative line. When is it the strongest? When is it the strongest? When it is more negative, that's the more negative line, or when it is more positive? It's the strongest. Just think about sledding down these hills. Like if you think about sledding down the hill, which of these would be the biggest hill for you to sled down? The negative, you're right. If you're like, wee, yeah, that'd be so fun. You just, that's one of those hills that's scary to sled down. More negative, the faster. Yep. So, and then exactly, it could be steeper either way. So the steeper the sigmoidal curve, the stronger the relationship. That's a good note right there, Philip. Philip, if you got it right there. The steeper the sigmoidal curve, the stronger the relationship. And if you think about this, we're looking at the coefficient of x1 right here. So this is x1's coefficient, and here it is up here. And think about this. x1 starts off negative. So if we were to put in a -5 right here and solve this out, then what's going to happen? We're going to do -5 times this, and then it'll become -2.5, and then we'll add it to this, and this will be -3.5. You would literally solve right here and plug in this value and solve out the implicit line, and it'll make that coefficient more negative. So it already starts out negative to begin with, and if we put a negative in for x2, it'll make it even more negative, and it'll be steeper. So the interaction changes the shape of the sigmoidal curve. So the interaction in logistic changes the shape of the sigmoidal curve. I'm going to look through all these slides, finishing up your guys' test, but things like that are very important to know, that an interaction in linear changes the slope of the line. An interaction in logistic changes the shape of the sigmoidal curve. And you can literally see things go from sigmoidal positive to sigmoidal negative as we do right here. So here, let me zoom in on this. Okay, so this is predicting whether or not somebody has diabetes. And we see right here their insulin levels. Now, is insulin good or bad? What do you guys think? Let's see. First person in the chat, 10,000 points, who gives the right answer. Is higher levels of insulin good or bad? Who knows? Visualize model. Brad right there, 1,000 points. Visualize model. Dennis says bad. Brennan says good. No one's got it yet. Wait. Well, wait. Brad's kind of right. Brad, you might have got it. I might give it to Brad again. If you look at these curves right here, we said, is insulin good or bad? Like, well, Brad, and so for having diabetes, though, for only this one right here. So higher levels of insulin. So no, but that's the thing. That's what we do in this class. That's what we do. You know what? Brennan, Dennis, and Brad, you guys each get the 10,000 right there. Taking a shot at this right here. I like it. So look at this. You ready? If somebody has large levels of glucose, higher levels of insulin would be what for their probability of having diabetes? Like, this is probability yes. So if someone has high levels of glucose, higher levels of insulin would be good or bad. If somebody has high glucose, then higher levels of insulin would be what? Follow the red line. Follow the red line. Good. So, but if somebody had very low levels of glucose, which you can see up there, sorry, it's covered up a little bit by that. If someone had very low levels of glucose, higher levels of insulin would be very, very what? If someone had low levels of glucose, small glucose levels, then higher levels of insulin would be very, very bad. Exactly. So wait a minute. The way in which insulin explains having diabetes depends on somebody's glucose levels. Like, it's like an interaction is always the way in which X1 explains Y depends on X2. So you can see this right here shows there's a very steep change. This one, there's some change, like the way in which glucose explains someone have, that would make sense because exactly. Because it's like type 1 and type 2 also. It deals a lot with that because if you have high levels of insulin, you should probably have higher levels of glucose. So would that make sense? Yeah. Somebody who has high levels of insulin but also has high glucose, their body seems to be in homeostasis. It might be the wrong word for that. I'm not a doctor. I play one on this YouTube channel. I don't ask me doctor questions. This is also statistically significant right here, and this is the drop 1 test. Hint, hint, that's a drop 1. Hint for your take home. Hint for the take home. Ask my brother. He might know. This is the drop 1 right here, and it's doing it for you with the visualized model. So this is the visualized model, and it will do a drop 1. So, hey, visualize those models. See what they show you. See if you see something on the take home. Let me ask this. You can't say which one, but did anyone find an answer to the take home by visualizing a model? Did anyone do a question on the take home and visualize the model? Be like, ooh, that looks like an answer to a question that I need to know. Hopefully the answer is yes, because there's there's at least one I can think off the top of my head. Yep. Visualize your models. Just do it. Always run your functions. I mean, even if it doesn't say visualize the model, just to take a look at it. Be like, what does that look like? Here's another thing we can always do. We can always look at the coefficients for the model. Boom, coefficients. And you can see here that there's a negative interaction, which says that look at this right here. When you look at the coefficient of BMI, as insulin increases, the coefficient of BMI, sorry, Brad. When we look at the coefficient of BMI starts off positive, but as insulin increases, BMI should get a weaker relationship. Okay, so let's go back to the graphic. Oh, wait, that's BMI. Oh, why is it got to be a different graphic? Oh, do we have the plot on the next screen? We do. Okay, good. So we have right here, BMI starts out with a positive coefficient. And here's BMI with a positive coefficient. But as insulin goes up, the coefficient of BMI should go down. We will do the Kahoot at like 3 p.m. tomorrow. That's my plan right now. 3 p.m. tomorrow, Kahoot. Stay tuned. And so we look here as insulin goes up. Here's the large insulin level. If you can't read, that says insulin large. And so when we go to larger insulin levels, we see the coefficient of BMI going down to where it eventually reaches a negative relationship. And just think about this. If you have a very high insulin level, then having a larger BMI is apparently a good thing. It just makes it less likely to have diabetes. And it's just kind of like if you're a bigger person, you should have more insulin. If you're a smaller person, having a lot of insulin would really bad. Well, this is BMI. As BMI goes up for people with small insulin levels, that would be a very, very bad thing. But as BMI goes up, if you have high insulin levels, that would decrease your probability. It just has a lot to do with the way the body, like certain things that need to be kind of in sync. Like if you have a high BMI, then you should have certain other things. So and BMI is not a horrible measure, but it's not a great measure. It's just if you look at the athlete's BMI, has anyone ever done that? Like if you look at like the BMI of like LeBron James or someone, his BMI will be like, oh, he's got a BMI that says he's not the right weight. And it's like, he's LeBron James. He's perfectly fine. So he's doing well. He's in top physical shape. But BMI is like, nope. Like, okay, this measure is not perfect in the way we measure things. It's not horrible, but it's not perfect. So I don't know. It's weird because I'll look at my BMI and it'll be like, you're overweight. And I'll be like, really? Really BMI? Maybe I am overweight. Okay. So what do you have going on right here? We've got one of our last little things right here. Let's put in some categorical variables right here. When it comes to categorical variables, we need to know that they have reference levels if it's a what type of variable. because we're doing categorical variables. Wait a minute, Brian, you said this whole chapter we're doing categorical variables. But now with a reference level, it's a categorical what? Who's got it for 1,000 points? Now with a reference level, it's a categorical what? Not the one we're doing with logistic. If it has a reference level, it's a categorical what type of variable? So if it has a reference level, predictor, Mila right there, another 1,000, you're totally right. Reference levels are for categorical X's, and we have references and indicators, such that when we do gender right here, the reference level would be reference level I am first, so it would be female. And then we have here 3 levels right here for this, so the reference level is agree. Because with reference levels, I am first, and that means the reference level is first, the others are indicators. So we have an indicator for disagree, and we have an indicator for neutral. And this goes by the rule, if you have 3 levels, you have 2 indicators because one becomes the reference level. So it's important to know the difference right here, that if you have 3 levels, you have 2 indicators because agree becomes the, it's so weird how like you do this and like your other fingers are like, I have to follow that finger. So with this right here, you can see we have an effects test again, hint, hint, hints. So this is running the drop 1 again, and we're looking at the effects test. There looks to be no interaction right here. If you need to include interactions, make sure you do. It's a hint for the homework. And we can see right here that there's a difference between the no and the yes. I think we include interaction here in a moment. Oh, I want to see. There we go. Here's an interaction plot. So the way I know there's an interaction right here is why. These 2 sigmoidal curves should never intersect. Just like parallel lines, parallel sigmoidal curves, if they're parallel, would never intersect. You can look at some of the previous ones way back when those intersect, but these do not intersect. You might be like, well, don't they intersect right here? If you were to zoom in, you would not see them intersecting because it's literally just the curve being shifted left and right. So there's no interaction right here. And you can see there's no interaction by looking at the terms in the model, and there's no x1, x2 term. So the only change is to the 50-50 breakpoint. It's just shifting the curve left and right. So we can see there's no interaction in this logistic model. When we see an interaction in the logistic model, we will see the curve intersect because the way in which x1 explains y, which is the sigmoidal shape, depends on x2. And we see the same thing for categorical variables. So this right here does have an interaction because we see the intersection of the sigmoidal curves. And it might be, yeah, it's pretty strong. It's decently strong. It means the interaction adds new information not accounted for. So once again, we hear our old interpretation that the interaction included in the model as new information not accounted for by the other variables, which is pretty good because interactions are made from variables. So hopefully they're pretty significant because they have a harder time being significant. So which of these, this is a great test question, because it's a true false, and then you could kind of understand and still get it wrong, but someone could guess it and get it right, have no knowledge and get it right. So yeah, true falses are kind of, I don't know. I put true falses, they're easier to write, but they're not the best test questions. So when we look at homeowner yes and homeowner no, I want you to do this first. Look at the coefficient of checking balance right here. Checking balance will have a stronger relationship for homeowner yes or homeowner no. Checking balance will have a stronger relationship for homeowner yes or homeowner no. And don't be confused by the decimals on it because these are both the same. You could think of them as the numbers they are. Correct, Brad. Correct. Because if somebody is a homeowner, it'll do what to the coefficient of checking balance? If somebody is a homeowner, it'll do what to the coefficient of checking balance? Like if you plug in homeowner yes right here and you plug in a 1, then this will become, and you know what? I have to show this because I think it just makes sense. We're going to take a screenshot here and show this because this is how you solve it. Let's hop here to the main screen. Okay. So what you want to do when you solve this, and exactly, they're saying in the chat, great job, chat, excellent work, is you want to go right here, and when you solve these lines, if you want to solve for homeowner yes, no, I thought I clicked white pen. Yeah, here we go. You want to go to homeowner yes, and you want to plug in, if it's no, what do you want to plug in for this? If it's no, what am I going to plug in? If it's homeowner no, what do I plug in for homeowner yes? If they're not a homeowner, what do I plug in for homeowner yes? I'd plug in. If they're not a homeowner, because that said homeowner yes, I plug in 0, yep. And so there we go. And now we just solve and we get, it's the logit, which, sure. No, we don't talk about this. I don't want to say that. But it's going to be e raised to negative 7.7 and then plus, okay, cool. I can just, wait, what am I doing? Yeah, cool. Plus 6.4 checking balance over 1 plus e raised to the negative 7.7 plus 6.4 and checking balance. And it is 0.00064, but I just didn't want to do those. Just pretend, just for this example, pretend that these don't exist. Just for this example, because we're just focusing in on the math right here. But now, what would change? We're just pretending it's this for the moment. What would change if somebody had checking balance yes? If somebody had checking balance yes, then checking balance yes, or homeowner yes, excuse me. Homeowner yes would become a what? Right here. Homeowner yes would become a what? If somebody is a homeowner, then homeowner would become a what? A 1. Exactly. Great job. Austin, 1,000 points right there. Great job. Good to see you, Austin. And Megan, and Brennan, and Nicholas. Excellent work. And so now, this right here is going to change the what of the model. This right here is going to change the what of the model. That right there will change the what of the model. Which, I mean, it's still kind of this. It's not, it doesn't, changes the 50-50 breakpoint, which is where the what is. And that's going to add to that. I'm doing some rounding. This is not exact math, but it's close. It's changing the what of the model. It's not exact. It's close-ish, though. What did that change right there? What Brian highlighted just changed the what of the model. He added that number to the where. That number was added to the where. Where was that number added? The intercept. Exactly. That number was added to the intercept. So we have one other number to change right now. This number right here is going to get added to the where. So think about where the other one will get added to. This number right here will get added to the slope. And so it's 4.6, I think. And we're just doing rounded versions. But who feels like this makes sense right here, that we have one equation for the homeowner yes, we have another equation for the homeowner no. And if you remember the coefficient changed from, here we'll put it in green, but the coefficient changed from this for checking balance to this to checking balance. So if you look at the coefficient for homeowner yes, this is the yes coefficient, and this is the no coefficient. The no coefficient is stronger. So the no coefficient is stronger because the interaction makes it weaker. Hopefully, who feels like that example made sense and you could solve this right here? You could solve the equations. Hopefully yes. Because we can see that the no is stronger right here. This black line is the no line, and it intersects. It starts out higher and then it goes down. So the black line has a stronger relationship. And if you added the 2, they equal 1. Is that correct? If we add the 2, I don't think so. Send me more on that, Brad. I'll look into that. Is that theoretically correct? Add the 2 what? Maybe. I do not know. That might be something I don't know about it. But that is how interactions work, and we do need to mention this. I've been alluding to this the whole time, that we're doing this drop 1. Now, please realize this is huge, and this is for the take-home. I keep dropping hints for the take-home today. So, look back on this lecture if you're stuck on some take-home stuff. When it comes to the take-home, if you are trying to figure out, so if you try to figure out the significance of of something in the model that has multiple things in it, drop 1 is the key. Take a note on that, and that's good for the take home. If you're trying to figure out the significance of something with multiple things in the model, you have to wrap them all up and drop them all out of the model together. And that's a drop 1, which is a partial F test, which is also known as an effects test. So an effects test can be done with the drop 1 function, which is doing a partial F for you. Is anyone being like, okay, this makes sense. Okay, I use this on the take home, and I know, don't say where to use it, but is anyone having an epiphany here? Or like, this is like, okay, definitely using this. And this is how you do it for logistic. I do want to point out that in logistic, it's not test equals F, it's test equals chi-squared. So in logistic, you have to do test equals chi-squared instead of test equals F. In regression, this would be test equals F. In logistic, it's test equals chi-squared. And this is how you see the impact of removing something from the model. So a drop 1, as we've talked about previously, is going to remove one thing out of the model, but it'll bunch it up together. And here, let's show a quick example of this. What I mean by this is if we were to make a model right here, and we'll do a logistic. So we're going to make a logistic model. We are going to predict somebody's gender from all the variables in the data equals, it's not going to load, but that's fine. Survey 10, comma, family equals, and then you have to go here and binomial. And then library reg class, data survey 10. You should do it in order technically, but I think I did it. Yep, there we go. We'll visualize them. Oh, can't visualize it, too many variables. We'll do a summary of it. It's going to look insane because we put a lot of variables in here. And here's all the variables. Now, one thing I want to point out right here is handedness. Here's handedness. So what is the impact of handedness in this model? What do I have to drop out of this model to look at the impact of handedness? To look at the impact of handedness, I have to drop what out of this model? How many things? To look at the impact of handedness, I have to drop how many things out of this model? I've just got it highlighted for you. And I can do that. I think it doesn't have the capital SQ. It doesn't, good. It's capital C. Because I don't think this one gives you an error if you do it incorrectly. And I always hate that about certain things. If it doesn't give you the error, I'm like, come on. I need to drop 2 things out of the model. So, sure, that's fine. Good warning. Handedness right here, woof. You know what's so interesting? The p-value of handedness is so insignificant, and it's left and right actually had lower p-values. I'm not saying they're good, but they were lower. But handedness has nothing to do with your gender. What variables add new information about somebody's gender? What are the most significant things in this model that give us the most information about somebody's gender with the other variables already in the model? And you see, it's so interesting because we've got some multicollinearity. I won't show that yet here. I'll show it next. But what variables add with them the most information about somebody's gender? Like, and it's not saying, oh, if you know this, you know someone's gender, but what variables with all these other variables in the model? Height, actually, Philip, I'm still giving you 1,000, but height does not add with it new information about somebody's gender. Height does not give us new information. Height, what if you told your friends, height is not significant in explaining somebody's gender with other variables already in the model? So height is not significant. That's one of the paradoxical things. If we were to make a model here of just height, so here we can do this. Let's make a model of just height. And you can see if we do just height, height will be significant. Height will be ridiculously significant. Here's a model of just height, and it's ridiculously significant. You can even visualize this, and you can see a very strong sigmoidal curve right here. And here's the ridiculously strong sigmoidal curve, which as somebody's height increases, 2 individuals who differ in their height by 1 inch. The individual who is taller is more likely to be male. One of these days, I'm going to remove that from Stat 201, and I'll never say the bad interpretations again. But I did learn to say those when I was in stats, and I do teach those in Stat 201, so they're in my brain. Don't let it be you. Don't say that. 2 individuals, and this is not otherwise identical because it's not a multiple. It's 2 individuals who differ in their height by 1 inch. The individual who is taller is more likely to be male. That's it right there. It's interpretation of that coefficient. But sometimes you learn something very early in your stat career, and it puts itself in your brain. And then I think, yes, Brennan, great job right there, and Brad, mentioning the really important things in the model. We're going to do the drop one right here. Take a look at it. It's just telling me it's doing 0, 1 because it's logistic. Sure, I knew that. That's why I wanted to fit it. If you look right here, we have the desired weight of individuals and also number of body piercings. So, but this doesn't mean somebody is, you know, this model predicted male or female. It doesn't mean somebody will be male if they have this, or they will be female if they have this. It's just talking about the probability that if you were to see multiple individuals who had 2 piercings and wanted to weigh 130 pounds, the model's probably, it's like, yeah, they're in the long run, you would see a lot of those individuals being female. So it doesn't mean they will be. It just means in the long run, if we were to look at repeated trials would show that the majority, or like 98%, would be female. So it's just repeated trials. It's not one individual. It's just, yeah. Is there a reason why the asterisk? Oh, yeah. This is barely not statistically significant. This is barely statistically significant. This is pretty statistically significant, and this is ridiculously. And I think they say down here where the cutoffs are. So here's where they do the cutoffs for these p-values. So you can see right here, the dot is below 0.1, below 0.05 is that actual the mark of statistical significance, below 0.01 is the double dot. And so Philip, 10,000 points. Thank you for asking that. I'm always liking it when people say, well, what does that mean in the output? It's just trying to clue you in. And you see my eyes automatically go to these things. When I ask, like, what's the most significant, my eyes automatically go to these. Like, I'm just trained to do that. I'm just like, oh, there we go, and there we go. Like, I forget that sometimes I haven't said that to everyone. Is there an application where the dot would tell us? Yeah, you know, it's the dot right here. These are things that, you know, you see we have all these percent more. So you could say, well, let me look at this in the simple world. And so here's this model in the simple world, and you see it is by itself, that is ridiculously significant. So think about this. It's at a really big party right now. Percent more attractive. This is how attractive people think they are. And look, sorry, gentlemen, or like, I don't know, congratulations, gentlemen, but 2 individuals where one individual thinks they're more attractive than the other by like 1 point. The individual who thinks they're more attractive is what? The individual who thinks they're more attractive is what? The individual who thinks they're more attractive is what? Which is it? It's so crazy. This is own personal, like, you think you are more attractive than other people, more likely to be male. Yep. 2 individuals who are otherwise identical, where one individual thinks they're more funnier than the other individual. Look at that. That's even stronger, I think. Wait, we haven't seen the coefficient. Yeah, that's when it reports. This is the smallest p-value you can get reported in R. If you notice, it's even smaller than this one. So, and look at the sigmoidal curve. It's even sharper. So 2 individuals where one individual thinks they're more funny than the other, the individual who thinks they're more funny is more likely to be male. So males think they're more funny. Males think they're more attractive. This is real data. I'm not just trying to say things. Wait, do males think they're more intelligent in general? Like, just looking at the simple world right here. Let's look at, do males think they're more intelligent? And the answer is, yeah. Oh my gosh. What is going on, guys? We think we're more athletic. Do males think we're more athletic? Like 2 individuals who are otherwise identical, where one thinks they're more athletic than the other. Yeah, that one's also super strong. We could look at the summary. But yeah. So I'm not saying. Brendan, you get 1,000 points for making me laugh. And this, what I really love about this is real data. It's just the data. It is what it is. But when you account for all the other variables in the model, those actually don't play a significant role. The funny one plays a role, but the other ones don't. And we do have ways of looking at this. No, we don't got enough time to do that. I'll finish this up. We could do the interactions right here. Oof, this is going to be ridiculous. Okay, let's just see what happens. Yeah, I think did we destroy it? Oh my gosh, that was a horrible idea. Don't do that. Don't do that. Don't do that. To look at interaction, we could do like height, star, handedness. And now we can look at the interactions right here. Oof, what is going on? Oof. Okay. Something in the background broke. And so we get the, yeah, it doesn't, ooh, it is actually almost significant. The visualize might be interesting on this. Whoa, oh, you know why? There's only like 2 ambidextrous people, or not 2, but there's very few ambidextrous people. And look at how that curve looks because it's trying to fit through the data. And so you see a change in the sigmoidal shape, but the limiting of the data limits the sigmoidal shape, the way it kind of draws the plot to go through the data. And yeah, so we see this much sharper curve. So ambidextrous has the strongest relationship. It's like, are you tall and ambidextrous? You're definitely a guy. No. It's so weird right there with that. So we should see the coefficient of ambidextrous if we look at the summary here being, it's going to have we're predicting probability of male. Oh, you see the other ones are all negative because ambidextrous is the reference level. Ooh, and all these p-values this is a weird model. Wow, look at how all the z-scores are the same and all the p-values are the same. I've never seen a model like this. I'm going to that's so weird. It's the weirdest model ever. It might be because I think of the lack of ambidextrous people. I'd have to look into this to be like, why does it look like this? But yes, one thing I do want to point out right here, please take a hint. This is a huge hint. This right here is the standard error in the difference from, well, let's talk about this one. This one right here is the standard error in the difference from right-handed people to ambidextrous. Hint, hint, hint for the take-home. Lots of hints today on the take-home. This right here is the standard error for the difference between ambidextrous people and right-handed. So that's the standard error. So we can use chi-squared if it's logistic, drop 1, and we use, yes, Brad, 1,000 points. Yep. If this had been, which we don't want to, if we do that, we want to go to this, and then this will become this. Here's the change right here Brad is talking about, and this should not have family binomial now. So now if I go back to doing regular old regression, which we've done before, because this is quantitative, this should run, and then we have right here, and look, it's a totally different model. You can see the interaction right here because there's a change in the slopes, and then we do the F right here. So now we've done it with a linear model. So great job, Brad. Everything right here is set up for linear model. You see the F and you see the LM, and then everything right here is set up for logistic right here. So here's logistic now. So pause the screen if you want, go back and look at it. This is logistic now, and you'll get stuff that, oh, wait a minute. Why is it not visualizing? Oh, wait. Sorry. Everything here is set up for, that's weird that actually gave me, there we go. Everything here is set for logistic. But wait, that was the problem. Sorry, I didn't see that right there. I thought I had everything. Yeah. No, Brad, 10,000 points. Thank you for that correction. I saw it pretty much as you saw it, because weight is not categorical. And so that was, you are very correct. And you are earning these points because I want you guys to correct me if I saw it right as you saw it. And I was like, oh, wait, I still have to have a categorical Y in there to do logistic. That's the key thing. That's what we started class with today. I was just kind of going back in time on the code. Brian, how could we possibly do one more topic? There's no way. Watch this. You're going to see it happen. We got 8 minutes. We got one more topic, and that's it. The last topic is just checking the regression. And it's so easy. Who's listening right now? Give me some yeses in the chat, because watch this. When we check it, we're going to talk about checking the fit here, and we'll come back tomorrow. Let's talk about it right here. You ready? We got this. We got 2 things we have to know. We can do this. So when we do this, we no longer have R squared. There is bye-bye R squared. R squared, no mas. No more R squared. We are now going to use the predictions. 1,000 points for everyone being here listening in. You're getting 1,000 points. Oh, you bet. We'll do a crab rave den class. You got this. So we are going to make predictions on whether something is yes or whether something is no. And Alex posted some stuff yesterday with this. So here we are. We talked about this. This is why I feel safe and that we got this. If it's actually A and we predict A, we've done it correctly. So if it's actually A and we predict A, we've done it correct. If it's actually B and we predict A, we've done it incorrect. If it's actually B and we predict B, we've done it correct. If it's actually A and we predict B, we've done it incorrectly. So it's important we know that we want to make right predictions. And we call this sometimes the on diagonal. This is called the on diagonal, and this is called the off diagonal. And I might show you something really cool in a second right here. Really cool that we found yesterday in 474. So when we look at this right here, in this model, we have 54 people predicted incorrectly right here, and 30 people predicted incorrectly right here. So this would be the misclassification rate. Does everyone see why these are the people who were predicted incorrectly? Now, the people who are predicted correctly are going to be the people right here. These are the people predicted correctly by the model. So you add them up, and you divide by how many there are, and that is the amount that the model classifies correctly, because this was classified correctly, and this was classified correctly, and you just divide by how many there are. This is the classification rate of the model. If you want to do the misclassification, you simply add up the ones that are wrong, i.e. this one, and you divide by the total, and that will give you the percent right here. So these are the wrong ones, and we divide by how many there are, and that gives us the total. So with this now, we have to think about one last concept here on this. What would the naive model do? And the naive model does not know any x's. All the naive model knows is the y variable, and the naive model would just predict the what level for one last 10,000 points. The naive model would just predict the what level for everybody. The naive model is just going to predict the what level for everyone. The naive model is just going to predict the what level for everybody. Majority. Exactly. The naive model is just going to predict the majority. So most people in this are what? Most people in this are what? Most people did what here? Most people actually have diabetes or actually do not? Most people actually have it or actually do not? Most people actually have it or actually do not? Most people do not have it. So if you want to look at the amount it gets right, it'd be this. And then the misclassification would be this. And you can't have a misclassification lower than 50% with the naive. Does this make sense that the naive does not know those predictions? The naive does not know the predicted values. The naive just knows the majority level. So we would just say, oh, most people don't have diabetes. Well, let's predict everyone doesn't have it. We'd get 262 people right. Most people don't have it. Well, let's predict everyone doesn't have it. We'd get the people wrong who actually do have it. So that's how the naive model makes predictions. Do not look at the predicted, because this is from the model. The predictions up here are from the model, which uses the X variables. The naive only knows just most people don't have it. That's all the naive knows. It's just like most people don't have it. Nobody has it. That's got that. That's just how we predict it, and it's showing some more models right here. Here's a model that is just using the naive, and it's the same as the naive. So this model that uses log income, which we saw earlier, it was that model that was flat. It was the model right here. This model's predictive capabilities is exactly the same as the naive because it predicts nobody donates. So when we look at this right here, the model is going to make the same predictions as the naive. The model makes the exact same. And the last thing you need to know, watch this, 2 minutes, is when we check the regression, all we do is we look at these p-values right here. You only have one real test to look at, and the only test, say this with me, this tests if the sigmoidal curve is a good fit. All it's doing is saying, is this curve a good fit? Put that in the chat because we got 2 minutes and we got this. All this test is to ask, is the sigmoidal curve a good fit? Is that S-shaped curve a good idea? That's all it's asking. Is that S-shaped curve a good idea? Let's see it in the chat. We got a little under 2 minutes. Is the S-shaped curve, specifically the S-shaped curve, is it a good idea? Is the sigmoidal curve a good idea? And the null is that it's a good idea, and the alternative is that it's a bad idea. So take a look at these two tests right here. Do we pass or do we fail these tests? So the test right here is the sigmoidal curve a good idea? And the null is that it's good. So do we pass or fail these tests? Look at these p-values and be like, okay, we what for the sigmoidal curve being a good idea? Do we pass or fail these? Exactly. Be careful. Remember, the null is that it's good. The null is that it's good. The p-value is high. That's why I wanted to pause on this. We will probably start next class with this, but this has everything for the assignments now. The p-values are high. Just let the null fly. So checking assumptions, so pass. Brennan, that's it. Remember how we check assumptions? If the p-value is high when we check the assumption, we pass the assumption? Because assumptions start out with that we're good. So every time we've checked assumptions in this class, we always start with the idea that we're good. So watch this. Here we go. How about for this test, do we pass on this test right here? Yes or no? We've got like 30 seconds. Do we pass this test for seeing if the sigmoidal curve is a good idea? Because all this is asking is the sigmoidal curve a good idea? And do we pass with that p-value right there? Yes. But then here's our friend who's a little more stringent. And do we pass with this one right here? Do we pass on this test right here? On this test, we do not pass the assumptions. So it gives you two tests, just two ways. Two different people looked at it. And here's two people who made up their own test, two different methods. Do we pass on the first test? Yes or no? Pass or fail the first test, asking, is the sigmoidal curve a good idea? And what do I mean by that? We're saying, is fitting this curve a good idea? This is the last slide. We pass that one? Do we pass this one down here? Do we pass that test right there, asking, is the sigmoidal curve a good idea? I might just literally put these slides on the test. Like I'm thinking about what to put on the test. I might just literally put like, do we pass both tests, one test? And you just look at it and you're like, oh, they're both above 0.05. We pass both tests. Sigmoidal curve was a good idea. And then you look at this one right here. Both p-values are above 0.05. Sigmoidal test, the sigmoidal pattern was a good idea. Please don't. Wait, please. So every time we check assumptions, we want the p-values to be what? Every time we check assumptions, class is over. Every time we check assumptions, we want p-values to be what? Every time we check assumptions, we want the p-values to be what? We want the p-values to be what? Every time above 0.05, exactly. And that's only with checking assumptions, because the null for the assumption is that the assumption is good. So anytime we do a check regression, we want high p-values, because low p-values with check regression is evidence of a problem with whatever we're checking. So we always start out with that the assumptions are good with a check regression. So when you run check regression, it starts with the null that your regression is good. And if you have a low p-value, it's evidence of something bad. It still means statistically significant. Like we have statistically significant evidence right here for this test that the sigmoidal curve was the wrong idea. So what is this p-value says we do not have statistically significant evidence by this method that this sigmoidal curve is a bad idea. This one we do have statistically significant evidence with this test that we ran that the sigmoidal curve is a bad idea. And these are just the gentlemen who made it, or might be women or gentlemen. I mean, I don't know. So Hosmer and Limshow, I do not know those individuals. I do. I have this book right here my dad gave me. This is Box Hunter Hunter. If a stats person is watching this, Cincinnati statue in the chat. I should have showed them this. This is a signed book by Box Hunter Hunter. My dad gave it to me. I should be careful with it. It is from, it's older than me even. That makes it really old. I should not make these jokes, because one of these days when I am old, I'll be like, it's older than me. And people will be like, wow, that's ancient, Brian. It's 1978. It's older than my brother, too. But 1978, to the memory of RAF, to Judy and GMC. They didn't even put the names. But you can tell my dad, all right, here, I don't know. Darn, my dad's still alive. Statistics for Experiments, Box Hunter Hunter. It's a classic book right there. Older than me. I like that right there. So George Box is a very famous statistician and hunter. Your mom's age? Wait a minute. No way. I got a thing in my hair. Brennan, was so you're saying your mom is, oh no, Brennan. No, Brennan, I'm feeling old. Oh no. Oh no. Oh, the first time a student had a parent who was younger than me, that was something I'll remember. Yeah, the student whose mom was younger than me, her mom had her when she was 15, because I was like, your mom's younger than me? And she was like, well, my mom had me when she was 15. So this is a while ago now. It's like 4 or 5 years ago, because I guess they were like 19 and their mom had them when they were 15, or like 19 or 18. So you think I was like 34, 35 or something, and they, their mom was like 33. So I mean, but that's all right. It's just it's one of those things in life when you start to these things start to happen, you start to realize you're older. And because think 10 years from now, I mean, I'll be almost 50. So when I'm like, oh, your parents are my age, I'll be like, yeah, Brian, you're 50. Oh, you remember the first time I had a sailor work for me who was born after I joined the Navy? Yeah, exactly. Exactly. Exactly there. Yeah, exactly, Brendan. You're right. Kids born in the year 2000 will be able to drink. So it's like, oh, you're born in the year 2000. Here's your beer. I mean, because it's legal now. So it's like, yeah. And there was a big thing with September 11th, like the children who were born on September 11th or being born after September 11th. And September 11th is 2001, but still, people will be able to drink who were born after September 11th. And I just have to remember sometimes it's weird because, like when I was a kid, like JFK's assassination was like so long ago. But what was JFK died in like 1967? No, 1969? When was JFK? I know, one more year, right? It's crazy. JFK assassination. What? What are you Googling on your computer? 1963. Wow. So yeah, that would be almost 20 years before I was born. He was born in 1917. He's the age of my grandparents. 1963. 1963. So that's later, Dennis. Oh, later, you're saying later. Was it 63? It says 63, right? Am I wrong? 1963. And with that being 1963, that's 19 years before I was born, which would literally, I mean, like, I know I thought it was later too. I thought it was like, yeah. Which is interesting because that means my parents were 13 years old when it happened. Like, yeah, I'm sure my parents remember it, but my parents were a bit younger when it happened too, because he's the age of like their parents. Like, I mean, he literally is, because my grandparents were born in the teens. Oh, really? Oh, yeah. Brennan, yeah, did they make a TV show from that? I mean, I'm saying, I know I should read books. I should really read. You know what I should do? With this time off that I have, I should be like, I'm going to read a book or two. I always say that and I don't read books. I'm like, I'm going to read a book. And then I'm like, I don't got time to read books. It's on Hulu, yeah, and it's got James Franco in it, right? Yeah, it looks pretty good. Maybe Chelsea and I will watch that. So, because she likes history a lot. So if it's got a lot of history, I mean, I don't dislike history, but she's a big history fan. So, and I like James Franco, so so like I think history's all right, but like we all have our different things that we're like, oh, this is my favorite. It's got lights on it. Moon landing was 69. Yeah, that's what I thought, because they were like, we're gonna put a man on the moon, and that was like a big thing. And then to know that he died in the 60s, because it was like, the race. Haven't had my history is all messed up. Yeah, one thing is like I didn't do well in history in high school. What I didn't like about history, I don't think I had a really good history teacher. I don't think I had a history teacher who thought of it like telling stories. And I've seen really good history teachers. And so I think if I had better history teachers, I'd like it more. But also, I was a lackadaisical student, and you can't figure out history. If you don't know history, you don't know it. So when it came to math, I could usually figure out math. Like I could logic out the math. I could be like, oh, this makes logical sense. And I'm always trying to I think that's why I enjoy statistics so much, is like, I'm always like, well, what does this output mean? And then I try to make it make sense. I want to know what every number means on this screen. Like every single thing in this code, like this is your Y variable, this is your X variable. There's an interaction with another X variable right there. And this is the data that we are using. So those variables are contained inside the data frame. Family is the type of regression we're doing. We're doing a logistic right here. Oh, thank you, Sarah. I appreciate it. Yeah, I know. Well, okay, maybe you're not talking about me. You're like, if Brian was a good teacher. But anyways, I'll stop assuming. Set seed controls the randomness, just a random number we're choosing. And then check regression is going to be used to check the regression, which we're doing down below. And then there's just two different methods we're using to see if it's a thank you, Sarah. And so yeah, and that's the thing is I want you guys to like this stuff. I want you to be like, okay, I like stats. There's some cool things we can do with it. And so I really appreciate it. We'll take a short break. But Sarah, thank you so much. And we will be back. But get ready, everybody. It's the last day of 474. we'll finish off here with some support vector machines. So 474, I will see you soon. We've got a new intro. Stay tuned.
exciting day in Stat 201.
Jason, no. Jason, no. Out of the shot. Jason. Mark, where is everyone? Why is everyone in the shot? This is Stat 201. No, Jason. Jason, no. That's perfect, Jason. Leave it right there. No, Jason. What? No, no, no. Jason, you're out of the shot. Jason, no. Hey, Jason. No. Why aren't you behind the camera?
And now, Stat 201.
Jason, no. Hey, Jason, no.
Get ready.
I love the Jason no. How's everyone doing? How is everybody doing this morning? Adam, good to see you. Jordan, good to see you. Madeline, Jacob, Sarah, good morning, everybody. You guys get 200 points for being here bright and early. 200 points in the chat. 200 points. Carly, good to see you. Jenny, good to see you. 200 points in the chat. Awesome. Good morning, Andrew. Peyton, good to see you. Yeah, Stat Nation, love it. Awesome stuff. My hair's getting so long. It's so funny seeing. It's just like, it's getting crazy, everybody. It's getting crazy. So, good morning. One thing, we did some cool stuff yesterday. We were talking about decision trees. And so we found this app online that this person created. And they're literally creating the visualizations. I think we did this during office hours. But they're creating the visualization and showing the distribution. I'm going to vanish. They created the distribution and visualizations of their decision tree and show the how the leaves are distributed, the nodes, the terminal nodes, or the leaves at the bottom. Lots of names for these things. But they show within, and it creates we could try to augment this. I don't know, maybe we'll do that during office hours. But we could try to augment this to different data sets because they have it working on their data set right now. It says like choose target variable. So they only have one variable you can choose where it predicts the categorical. But if we were to look at their Shiny app for doing this, you can see where we kind of get the plotting right here. I wonder, because where is, see, it's going to use iris, data equals iris. What if, we're going to try one thing real quick right here. We're doing this to start class just for a little bit of fun. I want to start class day with something fun. So when we run this, let's run the app. Let's see if we can get it to work on something else real quick. It works on species. So the Y variable is factor, iris, names iris, is factor, select, choose Y, labels, choice, Y choices. So you only get the one. See, what if we go in here? What if we do something crazy? What if we break their app? We're going to go right here. And we're going to go here to library, write class. Okay, let's try something crazy. Ready for this? We're going to try to just alter their app. It's probably going to break it. Probably not going to work. We'll give it a shot. And you see right here we have iris. So we're going to go right here. And the iris data is loaded in. I have a real quick question. When comparing two models like GLMNet and the k-nearest neighbors, when we look at the RMSEs and the standard deviations of 3.32, does this tell us that the k-nearest neighbor model is better? Model works better than the new data? Great question, Sarah. Great question to start out class 2. You're looking at the RMSEs. Now, if you have the RMSEs, because you're predicting a quantitative Y. So what Sarah's pointing out right here is a quantitative Y. Does everyone see that? Sarah is looking at RMSEs. She's just looking at a quantitative, which means she probably has her fit control is method equals CV, number equals 5, because we're not doing like the 2-class summary. We're not doing any of those things because we're doing a quantitative, we're doing a quantitative Y. So you need to look at the RMSEs and the what's for the RMSEs. You have it right there, the standard deviations. So what you would do is you would take your RMSE, I'll put it right here. So this is what Sarah will do, is she'll take her RMSE 1 minus her RMSE 2, and then you will divide those by the larger of the RMSE standard deviations. So you're going to take your RMSE 1 and your RMSE 2 and divide those by this, and this will turn their difference into a what for you. This will turn their difference into a what, Sarah. Between the two models, you will have now found a what for their difference in RMSEs by taking the RMSE for the first, the difference between it and the second, and then dividing it by the larger of the two RMSE standard deviations. Yep, that'll turn into a z-score. Does that make sense, Sarah? So with the standard deviation you've given me right there, that just tells me a standardized metric, and it should be the larger of the two. So whatever standard deviation you're using, RMSE standard deviation down here, larger of 2. So whatever the larger of the two. Does this make perfect sense to everybody? And it's how we can compare models. You can also do it with AUC. So you can do the AUC of model 1, the AUC of model 2, and then the AUC standard deviation. Does that help people make sense of it right here? All we're doing is just taking the difference between the RMSEs or the AUCs. Do we take the absolute? Either or is fine. Yeah, then notes. Anisha, great question, 1,000 points. Both Sarah, Anisha, and Jordan. Thank you for everyone chiming in here. Because it doesn't matter which way we subtract it. We're just trying to see if this value is bigger than what. With the z-score, it tells us if there's a statistically significant difference in the predictive power of the models. So you can only have one of two things happen right here. Scenario 1, or let's say scenario A. Scenario A is difference is less than or between, between 1 or -1, exactly. Difference is between -1 or 1. It's less than 1 so then if the standard deviation is larger than 1, how do we know which model to choose? The one that's better. So in scenario A, you would choose smaller. Wait, this is this. Doesn't matter. So if the z-score is between -1 and 1, doesn't matter. Bleh. Does that make sense? Because it's like, either or model they're both equal in predictive power. Who's following me with this? Like, and great questions right here. You guys ask questions, we give answers. So if the difference is between -1 and 1, you're saying they have similar predictive power. They're within one standard deviation of each other. So the predictive power of these models is virtually identical. And so nothing to see here. Move along. So nothing to see. It's not the droids you're looking for. I am not even a Star Wars fan. Difference greater than -1 or 1, or we can say outside of. And it doesn't matter if it's negative or positive because Nisha brought up a really great point. Boom. And Jordan's bringing up the next great point. Jordan, 1,000 points. Thank you, because that's exactly it. The difference would be the way we subtract them. You could always do the bigger one minus the smaller one and always get a positive number. But it's just like saying, is there a difference in how many free throws Brian can make in a minute and versus Darren can make in a minute? If you subtract Brian versus Darren, you're going to get a negative number because Darren will get more free throws than me. If you subtract Darren versus Brian, you'll get a positive number because Darren makes more than me. So Darren versus Brian, you're going to get the positive difference. So either way, we're just looking at the difference. And so it'll be positive if you subtract the big one first and from the big one first. And with this, this is lower RMSE better or higher AUC better or accuracy. We could put that in here too. Higher AUC or accuracy. They both work on higher is better. So when you have a statistically significant difference, or it's not really statistically significant, I shouldn't use that word because it's not p-value related. Z-scores are kind of, but we're only using a z-score of 1. So when you have a difference that is more than 1 standard deviation away in the predictive power of models, you will use the model that has either the lower RMSE, which is the lower typical miss, or the model that has the higher AUC, which is the way in which it orders the probabilities, that it correctly gives the yes class the higher probability this amount of time, or the higher accuracy if you're fitting the accuracy, which is the percent of time the model accurately classifies something into the group it belongs to. So it's important to know the RMSE, the accuracy, and the AUC, and we want these to be higher, and we want this to be lower. And technically, we don't do it in this class, but people do use MAE a lot. And then there's MAPE, mean absolute percentage error. I don't know, because I don't do much MAPE, but that's also, has anyone seen MAPE outside this class? But that's another one right there. Does this make a good bit more sense right here? Good stuff, good questions. Always ask your questions. We'll jump right into them because you guys know I love doing so many things and love showing you things. And we're talking about support vector machine. With that, we'll come back to this. Would that be, yep, a lot of this could be possible test questions. Comparing two models, knowing which model to choose and why. Yep, a lot of that, Kelsey, great questions. A lot of that could be test questions relating to how do we compare these models, which model do we pick and why. Very, 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 very important here. Let's drop into, and great questions. We're going to jump into support vector machines, and we will finish this up tomorrow, so I do want to start it now. Let's jump into support vector machines. And remember, this and the neural nets are a bonus assignment. So let's go right here. Got the notes. And let's jump into support vector machine. Let me go back and let's change screens right here. Here we are on support vector machine. I lost my mind there. So with this, there we go, look at that. With this support vector machine, this is where I just don't even understand. Neural nets will not be on the test. Support vector machines will be. Support vector machines, yes. Neural nets, no. Neural nets, no. Maybe there's a way I can make a neural net bonus question. I don't know. I'll try to figure that out. Neural nets are not on there as regular questions. Neural net is on the take-home as a bonus question also. Only the neural net stuff is bonus on the take-home. Support vector machines are regular. And so, but neural net is a bonus that can only help you on the take-home. But it's not on the actual test. And so, neural nets, support vector machines. Support vector machines are things that just completely blow my mind in what we've done in statistics. Support vector machines have a way they work where we're going to add an extra dimension to the data set. And we're going to use it right here to figure out, let me just show you fancy right here, an extra dimension. Now you might not be seeing that dimension, but let me show you it. If you take a two-dimensional space, where would you have to bring the data to make it to another dimension? Because I think this will put in your mind what's going on with all this. We'll go back through the notes. But if you have a two-dimensional space, where do you have to bring the data to in support vector machine? You bring the data to a what space? In support vector machine, we take a two-dimensional object and we bring it to the what world? This is just what's so crazy. I don't know who thinks of these things. We take a two-dimensional, so think about this. We're going to add an extra dimension. 1,000 points, who knows? We're going to take a two-dimensional space and bring it to the what world? A two-dimensional object will be brought into the third dimension. And here we see that same object being brought to the third dimension. I think we have, I might even pull it up right here because we can even put it in a 3D plot. But, because are we showing it? Where is it? I'm going to bring up the notes right here and show you it. Give me 2 seconds. I'm going to bring those notes back right here. Because we have a 3D plot of it, and it's just beautiful, and I want you to see it. So let me go in and grab those notes, because I really think, let me go here. Support. There it is. Okay. And I'll probably post this for everyone to see. Let's open this inside of R right here. Okay, install. I don't have those. Look at all those libraries we're using right here. And we have everything going. Installing stuff in. Let's go to the main screen. Okay. So we're going to take a look at this object right here in the 3D world and see how it's inserted in. And that's the key. I feel like this doesn't have anything. Okay. And object support for machine not found. Something. This is only this. Maybe this is missing it. Well, let's go back. What I want you to realize about support vector machine is that our goal with support vector machine is to find this extra dimension, because in the 3D world, we would cut through right here. In the 3D world, we're able to insert a hyperplane. And this hyperplane is a third dimension we are creating. So this X3 is a new dimension created. And this allows us to create the separation between these variables. And the way in which we find this third dimension is based on something called the kernel. So let's go back to the beginning here and talk about how we find this. Even right here, our data is in a what-D world. Even right here, our data is in a what-D world. Look at the data, only the data right now. Our data is in a what-D world. Our data is in the what-D world. It's not. It's only one-dimensional. It only has one X. Our data is one-dimensional. You might say, wait a minute, Brian, but it's a line. It's just 1D. Does that make sense? And then what we're using to separate it exists in a what-D world. The way we're separating it exists in the 2D world. This object is a dimension higher than this. So when you look at it in the 2D world, you'd actually see this. You'd be like, wait, that's a line now. But now we're kind of projecting it into the 2D world. So what is the goal right here? We literally take our data and add to it an object that is a dimension higher than our data. It's going into the next dimension. It's just insanity to me that we take right here this 2D data. This is 2D. Now I want everyone to imagine this. So we're going to have to use our minds and imagine this. Can anyone imagine this mountain like growing up like this and going? Can you see the mountain appearing in the middle right here and going like that? Who can see that? If you can see that, you're seeing it appear in a 3D world. And then what would slice through it? Now this is the mountain going downward, but then you would slice right here and slice off like that. And you'd have a 3D plane. So if you can visualize it, that's going to be a 3D plane in this world that's a 3D world that is taking place in this 2D world. Who thinks of this stuff? Who imagines like, let's add an extra dimension that creates a hyperplane? This right here is called the hyperplane. That is the hyperplane that creates the separation. And we'll talk more about what support and vector means in a moment, like why it's called support vector machine. So this right here is the hyperplane. This right here is the hyperplane. And this is the hyperplane visualized in the multiple world. So you see we have the square of x, and that's the way that we get, if we view it in the hyperplane world, we would see this right here. Now this is a dimensionality created to create the separation with the hyperplane. So the hyperplane right here exists as a kind of a line in its world, but then if you were to view it in its native in the, like in a 1D world, well, you can't plot a 2D object in a 1D world. It's weird because you would only see this intersection here and this intersection here. Like if this line were to be viewing it in its 1D world, it would only see an intersection here and it would only see an intersection here, which are the same exact points that we see here where it intersects and here where it intersects. So this is, if it could see the 2D world, it would see this. Here you have to imagine the 3D world, and you would see a hyperplane going through here where the points are kind of in a funnel, and then there's this plane going through it. So exactly, a plane, as Madeline says. So this is what we are doing. This is the whole goal of it right here. It's to figure out the support vector machine. And what do we mean by support? We mean the points that are going to create it. What do we mean by vector? We're just talking about the angles within kind of the algorithm. And then the machine is the algorithm itself. So let's take a look at this visually right here. Here's our separating hyperplane. This is what we are trying to make in support vector machine, is a hyperplane that creates separation with the variables. And we're looking at categorical data first and then quantitative next. So this will separate out and it will cause one group to be on the other side and the other group to be on the other side. So we're using this categorically first and then we'll use it quantitatively second. Here we are. There's a hyperplane. Just creates the separation, but it's usually not this simple to create a hyperplane that separates out the data. Usually we have to look at what points are creating it, because we could create any hyperplane we want. We could just be like, let's create this one, or let's create these. So which of these are the best? Now, all of these have a classification of what, or let's say this, have an impurity of what? All of these have an impurity of what? They have a Gini coefficient, they have an entropy of what? Their Gini coefficient and their entropy using any of these hyperplanes is which? Exactly, Vedrina. You're totally right. 0. They're perfectly pure. These are great. They have perfect purity. They have 100% classification accuracy. But which of these hyperplanes would be the best? So we have to figure out which hyperplane to use, and we do it this way. What we're looking right here is these points right here. It's going to be this point. Let me see if I can figure out which points. It's so hard to see. I think the next slide shows. There they are. It's this point, and that point right there. And what we're trying to do is we're trying to create, there it is, that point, and that point. And it creates the largest amount of separation between them. It creates kind of like this no man's land right here. We don't want points in here. This is a very bad area for them to be in because it's kind of the I don't know zone. And we'll have some like soft classifiers here in a second for this because we'll have tuning parameters to use for this. So what you're looking at right here is the support vector machine. These points literally create the support vector machines. These are the support vectors. They support the hyperplane. So the hyperplane is created by these support vectors right here. And we're going to pick the one that creates kind of the best kind of no man's land, the best separation. So there's a lot of support vectors we can use, but this one's going to be the best right here. So notice that the rest of the data is essentially not important. It's only the positions of the support vectors that matter. This means the procedure can be quite robust to outliers. Yep. That means it's going to be able to handle outliers well because it's only focusing in on a few points, and it's not going to take those outliers as the points we're going to use for the support vector. But we don't get these perfect problems. Right here, you see that the support vector is probably going to be something like maybe this point, I don't know, maybe this point, and then maybe this point right here. Like that might be the support vector we pick, which will create the hyperplanes. Oh no, I know, this is just like, we just can't create the perfect problems, Vedrina. Sometimes I worry when there's a sad face, like the stream stopped working and people are like, Brian, you disappeared. And I'm like, no. So, but we don't get these perfect problems. Like we'd love it if the world looked like this. It doesn't. That's not real data. But this is the kind of like quintessential problem. And the stars, yeah, you got it. It's like, oh my gosh, imagine making support vectors in the sky. You could probably do it. So what if the hyperplane doesn't divide the data into the space perfectly? What do we have right here? The support vectors. We have a soft margin classifier, allows some observations to be on the wrong side of the margin and even on the wrong side of the hyperplane. So when you look at this hyperplane right here, we don't want things like these points right here, that point right there. See, it's hard to see. This is a red point that is classified. No, wait a minute. This is the blue side of the hyperplane. This is the blue side over here. And then we can see right here, we have, I believe, this is a blue point, a red point that's classified as blue. And so that's a red point that is classified as blue. And this is a blue point that is classified as red. If we go back to our graphic right here, we should, yep, there we go. And we don't want that right here. And so we do not want these points to be in these areas right here. It's very, very bad. This is where we're going to have errors basically in our model, but that's all right. So we will work with this as a tuning parameter to say how many things can we have in this error range. So this C right here is very, very important. This is our first tuning parameter. Put in the chat for 1,000 points. C is one of the tuning parameters in a support vector machine. You need to know this for the test, that the C is a tuning parameter. The stars of the, oh, I'm so confused. So they're the support vectors. C is going to be the budget for misclassifications. So when we look at this right here, we're saying how many misclassifications can we allow? So larger values of C allow more misclassifications, and then we'll get more support vectors. So think about this. If we're saying, okay, we can allow for more misclassifications, we're like, okay, we could use this one, 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 this one. But when we have small values of C, we're going to say, okay, wait a minute. We can only use, like, if you have such a small value of C, you're like, okay, we can only have this many misclassified. And so you wouldn't get that many support vectors because you can't have high misclassifications. So the best value of C is determined with cross-validation. So once again, we're going to use the k-fold cross-validation process right here. And you can see over here, larger values of C yield simpler models, which may generalize better. And then we're going to, if we do a lower value of C, we're going to get models that are more complex and they could be overfit. So think about this. If you are saying that you want a small value of C, what are you saying you want for the accuracy of your model on the training data? If you are saying you want a small value of C, you're saying you want what? That's the hardest thing. Nitin, really good question. 1,000 points in. I don't know the right amount of C because it's like you have to balance it. You have to say like, okay, we're going to let the, and this will be AUC, it'll be AUC and I can't think of accuracy. So higher accuracy, lower misclassification, correct. If you have smaller values of C, you risk overfitting. With smaller values of C, you'll have lower bias. you'll fit the training data better with lower values of C. So lower values of C right here equate to lower bias. They could overfit the model because lower bias, and higher variance, obviously, because lower bias. So does that make sense that you're saying we need to fit the data really well, because C is going to be how many things we can have on the wrong side of the hyperplane. So when C is greater than 0, no more than C observations can be on the wrong side of the hyperplane. So what we're talking about here is how many points we allow to be on the wrong side of the hyperplane. So we'd get a bunch of C from all of these right here, depending on which ones are on the wrong side of the hyperplane for their respective category that they're in. So we're saying, okay, how many do we allow to be on the wrong side of the hyperplane? The more we allow, which would be a larger value of C, we're going to get more possible answers. So when we allow more things to be on the wrong side of the hyperplane, we're saying, okay, 20 of these things we're classifying can be on the wrong side of the hyperplane. So then we're going to have higher bias, but that means we'll have lower variance. Does that make sense? That if we allow more things to be on the wrong side of the hyperplane, the model will do worse on the data it's created from, but then it'll probably generalize better to models. Now, how do we figure out the right value of this? We're going to use cross-validation to see, okay, how well does it work on the cross-validation data or the validation data set? And then, of course, we'll check it with our test model at the end. Does that, who's following me with what C does? Because this is one of the big things. You need to know what the hyperplane is. You need to know what the support vector is. It's just the points that create the hyperplane. The hyperplane is created from it. What was the bias with high C? So when you have a high C, you're allowing for more points to be misclassified. The bias would be low. High C, lower bias. High C, lower bias because you're allowing for more points to be misclassified. Wait, did I just say that? High C, higher bias. Wait, I think I just said the reverse. High C, higher bias. Please correct me if I'm wrong. My brain just blinked. High C, higher bias because you're allowing for more points to be misclassified. Low C, lower bias because you don't have a budget for points to be misclassified. And you get fewer support vector machines because you can't create as many models or different things to try out. Does that make sense, Sarah? High C means higher bias. Small c, lower bias, higher variance. Exactly. Madeline's 100% right. Because when you have a small c, you're saying we can't misclassify points. So that's low bias. And if you have low bias, you have high variance you're more likely to have high variance. That's got it for there. This is a very important slide if you cannot tell. Like knowing this is a tuning parameter and it's how many we budget for misclassifications, and then knowing the bottom down here that larger values of C may generalize better. That is literally the idea of low variance. So larger values of C, lower variance. And since we said low variance and then loss of accuracy, that's saying higher bias. So it does say less accurate, but that means higher bias. Like a high bias model is less accurate. So even though it says less right there, think of it as like it does worse because it's less accurate. So it has more bias in it on the data it was created on. So here we are right here. We're seeing our classic picture. This is one of my favorite pictures right here. I'm going to find that other picture here in just a moment after we finish off the slides. But we are creating in this the hyperplane that will create the separation between the variables. So we bring it into a higher dimension. We'll talk about more about our choices of the dimension here in a moment, because when we talk about this, when we bring things to higher dimensions, we do get the curse of dimensionality. It means that taking things to higher dimensions becomes difficult. It just happens in this case. Sometimes it makes it easier. So as you add more and more dimensions, things get more and more similar, but we're just adding one dimension. So C is the permissible amount of misclassifications we have. Yep, the things that are allowed to be on the wrong side of the hyperplane. So when you look at this right here, Anisha, the ones that are on the wrong side of this hyperplane right here would have to be in the budget for C. For this support vector to exist, we would have to budget in enough misclassifications. So if you budget in a bunch of misclassifications, you'll get more support vector machines to try out, and the one that works best on the validation is the one that we will pick. So it doesn't hurt to try out higher values of C. It's just, you're like, just budget in how many you want, and the right value will be picked for us. So right here, we see once again a one-dimensional object being brought to the 2D world, and here it is right here. And then we see a two-dimensional object being brought to a 3D world. And you can't see 3D on here, but there is 3D, I promise you, because it would be just a funnel right here. And here's it in its two-dimensional world. If you notice right here, we're looking at x1 and x2, and then we've added to it a third dimension of x3 right here. So if you'll notice, there is a third x3 dimension right there. And I'm going to find that picture here in a moment. I'm going to make it 3D in R. So this is the big question. How do we find that extra dimension? How do we find the extra dimension in the support vector machine? We understand that all we're doing is just taking and going to a new dimension. Well, we're going to do what's called the kernel trick right here. And we can use different kernels. So all that this is going to do is the kernel is going to help us figure out which equation to use. The kernel right here is going to help us figure out which dimension to use to go into the higher dimension. And so now we have a few different choices of kernels. I'm going to go to the slide that shows the kernel choices right here, and I'll go back in a moment. But the kernels we can pick are the linear kernel, the polynomial kernel, or we can pick the radial, also known as the Gaussian kernel. So these are our choice of kernels right here, and you'll notice this in the assignment or on the take-home. We use the polynomial kernel on the take-home, I believe. You can use SVM radial, you can use SVM linear, or SVM polynomial. And so we have different things we can also tune inside of these. The order of D right here is something we will tune. So you can look at the different things we will tune inside of these right here. So we have 3 different choices of kernels. The kernel is just the mathematical trick we're going to do to figure out the new dimension. So when we figure out what is this new dimension, if you look earlier, for 1,000 points, what kernel did we use right here to figure out this new dimension? What kernel did we figure out this new dimension with? This was figured out via what kernel? So I'd love it if, this is just one of those good written questions to put on the test. Like, what kernel was used to figure out this dimension right here? This dimension was figured out pretty much. Phaedra Nuggets 1,000. And the answer is right there. It is a polynomial kernel. It's a polynomial kernel. Does that make, can you see up here what we did to the coefficients? And it is a polynomial kernel right here. So you can see how it works. We're just building a polynomial version of a new variable. Does that make sense right here? What is our new variable right here? It's going to be a polynomial version of the other variables to create a new variable in this model. It's going to be putting in some extra dimension to the data set. And you can see right here where we do the following. This is basically, if you remember from like sigmoidal curves, it's going to make something based on the Gaussian model right here. And then this is just some sort of linear combination of the variables. So right here we have the linear, we have the polynomial, and we have the Gaussian. And all it's doing is taking the original variables right here and figuring out some sort of new combination of them that is going to put it to a higher dimension. Just like x3 right here is a polynomial combination of the other variables. So x3 is some polynomial combination of the other variables right here. And I think, is this one's also polynomial. So this is also a polynomial kernel right here. It's just some of the easiest stuff to graph because the new dimension is just x squared. So this is also found by a polynomial kernel. So we can see some of these pretty easily right here and what we get. So it turns out that the equation for optimizing separating hyperplanes does not depend on the exact location or coordinates of the individuals in the hyperdimension space we are projecting into, but it depends solely on the entries in the kernel matrix, how we quantify the similarities between 2 individuals. Don't actually have to project each individual into the hyperdimension space, only have to compute the kernel similarities. Kernel implicitly captures the higher dimension space without explicitly having to construct it. This allows projecting into infinite dimension spaces when exploring the extents of separating hyperplanes. I know sometimes when I'm like, I don't think that slide has too much information because what we need to understand when we do this. Yeah, I love this slide. I can't describe it better than this. Like, I can't tell you a better way of saying it's just mind-blowing to think that we are taking something and bringing it to a new dimension. So we'll look at this right here on how it assigns the scores. And we can't really get those scores out very well. And I'm having some issues. Jordan and I are emailing back and forth. I might have to, let me say this in class right now. If you can't get the variable importance, because I know I've done it. If you can't get the variable importance out of the support vector machine, don't worry. Please take a note. Someone put in the chat for 1,000 points. Don't worry about variable importance for support vector machine. Do not worry about variable importance for support vector machine. And I swear I've done it. It's just one of those things. It's like not working, and I'm looking up things. I'm like, why am I not getting the variable importance out? Support vector machine's a bit of an odd model, Adam, 1,000 points right there. So don't worry about that on your take home if you're here right now. Jordan and I are emailing back and forth a little bit last night on that. And I was looking into it and reading up, and I'm like, why are we just not getting the variable importance out? And some people are like, oh, you have to use this thing and this package here and this thing here. And I'm like, and I'm like, I know I've done it. I've got things where I have it printed off in documents. I'm just like, maybe they updated something, or maybe I hallucinated. But but with support vector machines right here, I don't know, Jordan. I don't know. I know I've done it. I know I've got documents with it in it. I could, like, I sent you that picture where I'm like, here it is, and it's from a document I have where I've done it. I'm like, I've run it. And so I'm like, why is it not working now? Did something change? Things change, and then something doesn't work, something breaks. So don't worry about it. I mean, I spent an hour and a half looking into it last night, and if I'm spending that amount of time, I was going to send an announcement once I got it to work. I was like, I'm going to get this to work. Then I'm going to send an announcement. And I was like, okay, it's not working. Okay, whatever. We'll just now look at the importance of each variable in the support vector machine to help us kind of, and why do you look at importances? You look at importances to kind of give you insight for other models, to kind of know what variables are playing important parts. It just, if you have a lot of variables, importances can play a big role in, like, let me kind of narrow down my variables and kind of do a bigger model with more tuning parameters, but with fewer variables in it, because it's like, let me only focus on the important things. And that's why variable importances are important, because if you have, I mean, think about this. Has anyone ever heard of a data set with like maybe 1,000 X variables? This happens all the time. We call them would be very wide data sets. So you could have very wide data with lots of X's. Like, you might not have many rows of data. You might have very wide data, we call it. And so if you run into data like that, you might need to limit your X's. You might need to say, like, let's only focus in on these X's, because you'll run out of the ability to use your X's. So importances can really help you with that, to be like, what are the important variables? And you could try out different things. So we have to pick our support vector machine. So the reason we pick the support vector machine is the support vector machine controls the way in which we create the new dimension. So if we pick linear, we create a linear new dimension. If we pick polynomial, we create a polynomial new dimension. If we pick Gaussian, I just call it Gaussian a lot of times, we pick a Gaussian new dimension. So the way in which the new dimension is created is based on the kernel we pick. Pick a certain kernel, get a certain new dimension out of it. And here we see just a few different ones right here. This is some good stuff, looking at the radial basis kernel. And you can look at the ones that were misclassified. If you zero in, it's a little hard to see. We got the 2 points right there. And that right there that's a red point, I believe, because it's got an X on it, which means it should be misclassified. And so we've got here red, and we've got here blue, and this is the red region in here. And so we should see these 2 points bleeding out right here. Is that them right there? I think it's them right there. Yeah, there's the 2. Is that the one right there? We should see misclassifications along here. So hard to see sometimes unless we can't zoom in today. But we see, and we look at another one right here. Do we have the other picture? Because here we go. There we go right there. Well, it's saying this misclassified. I feel like it's not the same picture for some reason. I think it's just the way it's squished. But we do see some misclassifications along here. It's just because the way it's making it. So we see some misclassifications, but it's really good. And this is just the visualization of the misclassifications right here. So this is the big notes on it. If you can't tell, we're almost done. Support vector machine. As I said, there's not too much to learn on this. There's not too much to know. It's kind of one of these things that's too good to be true. The main considerations are what kernel to use. Are we going to use the polynomial? Are we going to use the linear? Or are we going to use the Gaussian? Why not just try all of them? You can try every single kernel right here and just go through and see which one works the best. So if you notice, the kernel is a huge choice. The kernel is going to pick the trick you use to bring it to a higher dimension. So whatever you create, the separating hyperplane will be created via the kernel trick right here. So whatever you pick will be picked via that. What parameters of the kernel should be used? When we have the polynomial, we have the degree right here. When we have the radial basis, we have the gamma, and we highlighted that a moment ago. And we'll also have the cost parameter right here to control for. So think about this. All this is saying is step 1 right here, pick your kernel, which you can run all 3. So you have step 1 right here, and then these 2 other things down below are just talking about the what's for the kernels you pick. These last two things are just talking about the what's for the kernels you pick that you have to think about. Once you pick your kernel, which is the trick that you'll create your hyperplane to separate out the data with, once you pick that kernel, then you only have to think about the what for that kernel. 1,000 points, who knows? Boom, Jordan, right there, the tuning parameters. Yep, that's it. Pick your kernel. This is pick your kernel right here, and then pick your tuning parameters. And the tuning parameters, like the degree is for polynomial. The tuning parameters for polynomial is degree, and then we also have Gaussian has the gamma, and we see that right here. We'll go back to the tuning parameter page again, but we see for the Gaussian, we have this gamma right there, and then the degree is right here. So we do have to tune the degree and the gamma for either the polynomial or for the Gaussian. So this will be something we'll pick the best value of this based on a grid of values. So what is the best value of gamma? I don't know. Depends. We'll figure it out. What's the best value of the degree? I don't know. Let's tune different ones and see how they work. There's no tuning parameter for linear because it's just a linear model. And I think you'd pretty much get the linear out of this by doing a degree of 1. So you could probably skip linear and just go to polynomial and tune it across a vector that has 1 contained in it, because then you tune a linear to it. So this right here, we've got the cost, the penalty proposed for separating the hyperplane. Larger costs make the model fit the training data better. There we go right there. And so when we think about a larger cost, and we also have this cost parameter right here. Now the cost right here is not going to be the soft margin classifier. I think this is where some confusion comes into play. We have a cost parameter. So this is not the amount we allow to be misclassified. This is a cost parameter. So you have to watch out. You've got the soft margin, which is how many we budget, and you've got the cost parameter. So when you think about the cost parameter, larger costs make it fit better. Be careful. Please, someone put this in the chat for 1,000. Put in misclassifier, soft margin misclassifier versus cost. And you have to be very careful when you're looking at what we are using. Are we using the soft margin misclassifier versus the cost? This is where people have seen confusion, because they both start with C, and sometimes they're both abbreviated as C, because someone will just be like, oh, C, soft margin misclassifier. And someone will also use C as the cost right here. So the cost is going to be how much does a misclassification cost us? And the soft margin misclassifier is how many do we allow to be misclassified? So be careful, especially on the test. Hint, hint, hint. I've already been writing the test. When you look at the soft margin misclassifier right here, the soft margin misclassifier is how many things will we allow to be misclassified. So if we allow more to be misclassified, we will have higher bias and lower variance. So if we allow more things to be misclassified, like we're saying we can make more errors, that is literally saying we will have more bias. But when you look over here at the cost, when you get to the cost on these models, it's different. The cost is going to be how much does an error cost us? The penalty when we get a misclassification. So this is a cost now. And so if we put a higher cost on it, the model will have lower bias. So now it's the reverse, and that's where the confusion hits. It's saying if penalties cost us a lot, if it costs us a lot, we would make what types of errors? If errors cost us a lot, if there's a large cost for errors, how many errors are we going to make? If there's a large cost for errors, how many errors are we going to make? If there's a large cost for them. If errors cost us a lot, if we put the cost way high for errors, yeah. And there's a lot of ways to use it. Oh, it might be, is it sequence negative? I might need to look at, is it a negative sequence or is it negative? It depends if it's using C as like, yeah, the cost parameter. And that's where the confusion always hits, because it's just the way people coded it, because some people use, yes, if we put a large cost on the errors, we'd have very few errors if we put a large cost on them. So large cost is going to make for smaller bias, which would mean we have less error. And I've seen this, I try to think where students have had big questions, because in some of the algorithms, it uses C as a cost parameter. And then in some of the algorithms, it uses C as the soft margin misclassifier. So please notice that, like we spent the last 5 minutes talking about this, that is either going to be C is going to be the cost parameter, which when you have a high cost, you'll make fewer errors because you're saying these cost me a lot, so I'm going to make few errors. And then if you use C as the soft margin misclassifier, you are saying this is the amount of errors I can make. If you allow for more errors, you're going to have the example on slide 40. Here we go right here. Yep, and I believe, yes. This right here, perfect. This negative right here, exactly. And this is being used as a cost. Now let's bring this into R real quick here, and you'll see, this is what I'm going to point out. So what it is, so high soft margin mix classifier, high biased. Yes, Sarah, you're right. And be careful, that is the soft margin misclassifier right there. And I think I might need to make sure it's very clear in the questions I've been writing. So that is, and I should probably not just say C, because it needs to be clear, is that the soft margin misclassifier, or is that the cost? And so this right here is going to be the cost. This is the cost. I know it says C right there. It's so confusing, but, and this is why we pause on these things, because this is where I've seen the errors and students have asked questions. Now, this is not -1 to 2. This is the cost. And the cost right here, was it unexpected? Did I put one too many? Good, it worked. This, when we look at this, let's look at the vector of it. There you go. It is the sequence of -1 to 2 by 0.25, and it's 10 raised to that. So that's what I was trying to say right here, is it's not quite -1, is this right here is going to be the cost, and we start out with a very low cost, and we go up to a very high cost. Which of these models would be most likely to be overfit? Which of these models, the model with a C of what value is the most likely to be overfit? Which of these models is most likely to be overfit? The one with a C of what? Who knows? Should be, let me double check because my brain's saying the reverse. It should be 100 because we're saying this is the cost of making an error. And if it costs us a lot, we'd make very few errors because we're saying every error we make costs us this. So if we say this, in a singular error costs us $100. If an error costs you $100, how many errors are you going to make? Every error you make costs you $100 on the test. How many errors are you going to make? A lot or a little? Every error you make costs you $100, and that's what the C right here represents. Since every error you make costs you $100, you're going to make less errors. Here, every error you make on the test costs you 10 cents. How many errors are you going to make if every error costs you 10 cents? I'm not saying you will make these, but you'll be like, no, you know, it only cost me 10 cents. I mean, not that you should just throw away 10 cents, but here you'd make more errors because the cost is lower. So in the lower cost models, we will see higher bias, lower variance. In the higher cost models, we will see lower bias, higher variance because these errors cost us a lot. Be very careful. I know the notes say that C is the soft margin misclassifier. It's known as that, but C is also used by the algorithms a lot of times as the cost. And the way we know it's the cost is because these are not, especially we know because it's not whole numbers. So this is being used as the cost tuning parameter, which is where we see on the slides, right? It's being used right here as a cost tuning parameter, and we see that right here. This is, let me hop back to this. So we have a few things we're tuning on. We're tuning on the degree if we're doing the polynomial, and the gamma if we're doing the Gaussian. And then also we need to tune on the cost parameter. There are ways to tune the soft margin classifier, but we don't always tune on that. But that is the amount it budgets in, and we can tune on that with some ways. But a lot of the default algorithms do tune on the cost parameter and the degree and the gamma. So please note, and does that make sense, Jordan? That C you are seeing, I know in the notes, I know that causes confusion because I've seen it every semester. No, that's why I'm like, we have to make sure we know this, that the C we are seeing is this right here. That C you are seeing is the cost. Which C though? I'm sorry, that's where the confusion comes in. Do you want to talk about cost or soft margin? Cost or soft margin? Here, let me write it down too. Cost or soft margin? Which one do you want to talk about? Why can't it be both? So, okay, we'll start with cost. Okay. So when we talk about cost, when you see cost, if cost goes up, then, here we'll go, wait, I don't have enough room. So if cost, and we'll do soft margin next. So cost, and either of these can be called C, which is the confusion. So if cost, my horrible handwriting. if cost goes up, then what would happen to bias? And what would happen to variance? So if cost goes up, then bias is going to go down. And variance is going to go up. Let me think right here. Yes. Because it's going to cost us a lot to make these errors. So if cost increases, the bias will go down because it costs us a lot to make these errors, but we'll get a high variance model because it's probably going to be overfit to the data because we'll have high cost right here. And then soft margin. This is how many can be on the wrong side of a boundary. So cost is literally how much does each error cost us, and soft margin misclassifier, also known as C, is going to tell us how many can be on the wrong side of a boundary. If we were to increase soft margin misclassifier, then we would increase the bias. And just think about literally what soft margin misclassifier is. Soft margin misclassifier is saying if this is the red side and this is the space pen side, then we will allow more points that are misclassified. That's what the soft margin misclassifier is doing. It's saying there can be more points on the wrong side of the hyperplane. Does that make sense what soft margin misclassifier is? It's more points would be on the wrong side of the hyperplane as we increase the soft margin misclassifier, which is literally higher bias. Like the model will do worse, but we get more support vectors out of it because we can make more possible separation between them because we're allowing for more mistakes. So soft margin misclassifier is basically your mistakes. And if you increase your mistakes, you increase your bias, but then we might get models that kind of work, about the same. Like it's like we don't overfit it to the data. So the cost parameter is how much does each error cost us, and always think about like money for that. Can we do like a yellow pen? So think about like dollar bills for this. So that one is like, how much does it cost you? And if it costs you a lot, you're not going to budget many errors. And you'd be like, oh, each error costs us $1 million. Oof, we can make no errors. We can make no errors on this. But if you're like, each error costs you a penny, you're like, each error costs us a penny. Well, now since it costs us so little, we can make tons of errors. So if you had a very low cost, what would be the bias to the model? If the cost was very low, bias would be what for the model? If the cost was very, very low cost, then the bias would be what? I'll disappear. Boop. Hopefully this helps make sense, this graphic help. High bias, exactly. Does this help people make sense of it? Who feels like they kind of get it right now with this graphic right here? Like we've got the soft margin misclassifier right there, which is the amount of points we can allow to be on the wrong side of the hyperplane. And we've got the cost up there, which is literally like the dollar amount each one costs us. Awesome. Thank you. And always ask. Keep asking questions. This is what we do. And I try to graph it out. Hopefully it makes sense because I can say it a bunch of times, or we can try to put it to a visual and we can literally see what the soft margin misclassifier is doing, that it's wrong, things that are on the wrong side of the hyperplane. That's the budget for the things on the wrong side of the hyperplane. You're welcome, Yaji, and you're welcome, Jordan. And then the cost is literally like a cost. Like how much is it going to cost us? And if it costs us a lot, then we're going to do low bias. There we go. Great questions today. We got so much time. SVM. There was part of me that was like, we could do neural nets. And then there was part of me that was like, no, I don't want to rush it. Never want to rush it. We got so close. Man, we could almost done it all. We could almost done neural nets. But no, I don't want to rush it. Don't want to rush it. I'm not going to rush through material. We're not going to do that. I'm not going to burn through slides. Support vector machine creates the hyperplane. Oh, wait, we're on the right side, right? Yeah, cool. It's based on a few points. And that's the problem is like, it's like a con to it. It's like, okay, since it, don't love it. I mean, that's one problem with it. So solution, the problem, the boundary between classes may not be well described by a straight edge, protect the data in a higher dimension. As we keep saying, that's all support vector machine does, is create the higher dimension. Okay, so now let's look at support vector machine with regression. And this is where my mind is just, I said my mind is blown, but now it's just like, my mind is blown across different dimensions. Like it goes from like, that's insane to, I don't even know how to tell you how insane that is. Because, and I'll show you the graphic that just does it for me every time I see it. This right here, we're going to take, and did we remove that? You know what I'm going to do? You know what I'm going to do? Because I know the slides have it, or they used to have it, and then we said there's too many slides. We said there's too many slides. We can't possibly do all the slides. And I don't like that choice. We did that last semester. We said there's too many slides. Because students would say in the review constantly, they would say they go too quickly. So we're like, okay, let's eliminate slides. They'd say it in my reviews too. They'd say, he goes too quick. And people probably still think he goes too quick. So here, let me pull up the, what? Okay, one more try. I've got one more try to find this. You ever think you just have a dream? It's like Inception, like everything's a dream within a dream. Has anyone here not seen Inception? If you have not seen Inception, go watch it tonight. Inception was one of those movies that I watched and I couldn't believe it after I saw it. Like I was just like, whoa, this movie has changed my life for forever. And so here we go. How many slides is this? 76. Cool. Awesome. Am I the only one in the class who's seen Inception? I was like, Brian, it's an old movie. I know. It's just like Inception, so good. Inception. Watch this. Ready? We're about to see the old slides now. I might even post these for you guys. Oh my gosh, a picture we hadn't seen before. Did I dream it? There. Told you that picture exists. Go see it, Jordan. Check it out. Oh, Matrix is great. Oh, I saw Matrix in theaters. I'm that old. I saw it. Did I see it opening night? I don't know if I saw it opening night. Remember how I kept telling you, imagine this in the 3D world? I'm going to start bringing back the old slides. Imagine it in the 3D world. No more. You can see it in the 3D world. There it is in the 3D world. Boom, you see it right there. We've got the 3D. Tenet is coming out. Ooh, let's check that out. Is that Doctor Who? I think so, right? David Tennant? Or maybe that's not the movie I'm thinking of. So you can see as we bring these to the higher dimension world right here, that you can see all we're doing is taking a 2D object and bringing it to the 3D world. That's all we're doing. This hyperplane right here now exists in a 3D world. And you know what? We're going one better on this because we've got a good bit of time today. We're going to literally view this in right here. Let me pull this up and I should be able to. I'm going to start using this class because we made changes and then you teach a class for like 2 years or something and then we make changes and then it just, It's like I have a script in my head that I know I'm going to like say things and I'm like, wait, that picture's gone because like I know the slides in the order they appear and then they don't appear in that order and then I get confused because I'm like, wait, that slide was here. It doesn't work in like the morning when I'm like, wait. Okay, so no separating hyperplane with the figure. This is literally what creates it. Kernel trick. I think we're well beyond it. Okay, let's do this. Watch this. We're going to do some magic. That should work. So we should see pictures appearing. Yes. Yes. Okay, wait. Was I literally one picture before it? I think I might have been. Okay. Because I just want to make the 3D picture. That's all I want. No. Well, at least we'll get to see this. So many pictures. Okay. Maybe I hallucinated that the 3D picture existed. Okay. That's what we were doing earlier today. So this is the 3D world right here. And now let's see what we're doing in the regression world. Let's take a look at the regression world. In the regression world, we're going to use the hyperplane to literally do this. And this is the picture that just blows my mind. I have to see this picture again. Because there is some way to create a linear relationship here. Between this X and this Y, there exists some projection in a higher order space that would create some sort of transformed variable right here. That it's x squared times sine of x. It's like, it's bringing it to the higher dimension and it's creating from a non-linear relationship. You remember back in regression? I know some people took it just recently here. You remember back in regression, the whole point is to have a linear relationship, right? And you'd say, there's no linear relationship here. And you're like, well, what if we bring it to a higher dimension where we make a transformed x? And that's why we say things like in 320, especially, I'm like, finding the right transformation is a hard thing. Well, this is going to search for the transformation for us that this transformed variable would create some sort of linear relationship within our variables. So now we will actually have a linear relationship. So what is the point of the transformation or the kernel trick here? The kernel trick is going to find a higher dimension for our x's. Now this is a simple x or one-dimensional x, and it's going to find the higher dimension that creates a linear relationship so that we actually have a hyperplane that goes through it, i.e. a linear relationship. Does this blow anyone else's mind that people actually thought of this stuff? They're like, let's project this into a higher dimension. And so Nitin especially, what do you think about all this stuff, Nitin, right here with like projections into higher dimensions to create a relationship that can be well described between the y that is linear? It's very matrix algebra-y, I would say. It might be like, I'd be very interested to see if Nitin's seen any of this stuff. I mean, the big thing about statistics and mathematics is that statistics is just the utilization of mathematics to solve problems. It's a very applied mathematical field. And so we, fortunately for us as business analysts, don't have to solve these problems. We just have to understand how it works. And that's why I keep reiterating, all we're doing is taking this relationship right here. And who can finish my sentence? The whole point with us doing support vector machine, what's the point of bringing it? That's you got it, Sarah. That's the question. What's the whole point of bringing it to a higher dimension? What was the whole point of this right here? What is the whole point of it? And it's right here. That this is the whole point of it right here. That's the whole point. Because we can now do a regression on it. Now, this is well described by a line. Exactly. So all of a sudden, we take something right here that is not well described, and boom, we have linear regression again. And we found the higher dimension right here that actually makes it work. How will we find this higher dimension? Don't worry, it's not too crazy. The answer is not too far off from what we were just doing. How will we find the higher dimension? Yeah, exactly. Nitin is totally right. And we'll have and we have interpretation costs too, because these are very, the interpretations on these are completely crazy. And so when we do this right here, one of the three kernels, Jordan, exactly the kernel trick. How do we find the higher dimension? The kernel trick. Literally picking the right kernel, picking the right tuning parameters for the kernel. Like, how do we know how to make this? Well, we'll pick a kernel and we'll pick the right tuning. We'll use tuning parameters through the kernel. So that's all we're doing right here. And we see right here, this right here is the soft margin misclassifier again right here, the errors. So we're allowing things to be on the wrong side. Back. So we have the soft margin misclassifier right here. I need to mute myself visual thing too. Larger values of C right here. This is the cost. We can't make clear again what the cost is. So please read again. Larger values of C. Focus the attention towards the errors made by the model. The result will be a model that has low bias. This is what we repeated endlessly. Because if we have a high cost, then the models will have very low bias because we're saying there's a high cost. Small values of C. And I realize, because let me even Google through these notes, soft margin, and we should see the soft margin misclassifier. Here's where the confusion always hits. It's just that this is called C, and then also we see cost. I'm so sorry that the cost parameter is also called C. This is what I want you to know, though. I will call this either soft margin misclassifier, or I will call it cost. I'm very sorry that both people are like, we want to call this C, and someone else is like, we want to call this C. There's only so many letters in the alphabet, and it just so happens in this set of notes, this is where the biggest confusion hits, is that we have the cost and we have the soft margin misclassifier, both known as C. Sorry, why'd they do that? They need to fix that. Whoever made this, one of them needs to pick C. Only one of them can be the real C. The optimum value of C is chosen via, once again, the cross-validation. So every time you see this right here, there was a question on one of your assignments, like how will we figure out which model is the best? Cross-validation. Once again, we're also going to tune the gamma parameter or the degree. So here's our other tuning right here. This is what you see that Jordan was pointing out. We'll just show this again real quick right here. Anytime you see this right here, like in the sequence, so if you look at this tuning grid right here, I know, right? They're like, we want C, and they're like, no, you can't have C, we get C, and it's like, come on, what are you doing? So we have here the sigma, and we have here the body fat, and so sigma, there we go, and the C right there, and this is the SVM radial, which they're tuning that on. That is what they're calling it sigma in this, but that's what we call the gamma. It's just the way people write in the equation. Very sorry for all that. It always drives me nuts when they change what something is called, but you see right here, we are tuning on the sigma, and that is going to be the different values of the lambda that is being used, and that's what they call it via this way. That's what just the person who wrote the algorithm decided to call it. And the C right here is going to be the cost. So we have here tuning of the SVM radial, and that is going to tune the gamma, and that's just the mathematics. And then someone wanted to call it sigma in their model, and then we're going to call this right here the C right here. And I will show you something else here in a second. But we're pretty much, because all we're doing right here is if you look at the different costs, and you can really see what's going on right here with the cost, this one right here has the higher cost. So which one of these is more likely to overfit? The red or the black? Which of these could be overfit to the original data it was made from and would not generalize well to new models? The red or the black? Which of these is more likely to be overfit? The red or the black? Red. It's fit a lot tighter to the original data and might not work as well, and it has the higher cost because it costs more for it to make errors. So the red is more likely to be overfit to the data it was created from. And so we see that right there perfectly. We've got the tune SVM right here. This is just one way of tuning the SVM. Here's the epsilon, and here's the gammas right here, and here's the cost. So the cost equals this and the epsilon. So this right here ranges everything good. We don't use this method so much, the E107, and this is why you see in the notes things like the epsilon right here and the gamma. So it's just what people name them and just what we're tuning on. And method right here, just the different methods within the care package. LS support vector machine radial. That's they're going the support vector machine radial. So once again, using the radial bias kernel allows you to tune on regularized parameters tau and the gamma parameter, which refers to as sigma. It's so confusing. I'm very sorry because it's so confusing for even me when it's like it refers to this as sigma. It's just, that's it right there. It is the gamma parameter, but it refers to it as sigma. Apparently, this is the classification according to the website, even though least squares is built into the name. So just knowing the different methods right here, especially with the different things, important slide, pause the screen now, take a look at it. Method SVM radial right here uses the radial bias kernel and allows you to tune on the gamma parameter, which it refers to as sigma, and the cost as C. So it's very important to know for the classifier regression. We'll use this, although it does not allow you to tune this right here, threshold, which errors account for. And this is the error right here. So that's the soft margin misclassifier, also known as C, but it's basically the errors. Oh yeah, let's try to do that. Jordan, we'll do that at the very end here. Let's do that. And there we go here, support vector machine, and the probabilities, pros and cons, and neural nets. We're not doing neural nets, so we divided the notes out. I think that's got it. That's why I was like, the notes are really long. I was like, I can't imagine what comes after this. So pros and cons, models nonlinear relationships with ease, actually solves the problem it's trying to solve. We can give the cost. We can do different things right here. It's automated, and the kernel trick solves for the equation. Sparse, easy to store and make predictions. Not too much tuning required. Strong mathematical and theoretical foundation. Cons, output class labels and not probabilities. No confidence intervals. While strong model, often not the top performing, and can be very, very slow. So support vector machine's all right. It's a choice. That's why it's at the end here. Because guess what are probably much your top choices? I wish Petrie would appear. Every once in a while, Petrie pops in. I think he's on a road trip right now. But we were debating over the best models. If you could only pick one model, what model would you pick to use? Let's take votes and then we'll do a speed run of the important stuff from support vector machine. Brian's going to like literally do maybe GBM. GBM is a good advanced model, or XGBM, which let's mention that briefly here. So, and I do need to mention one more thing, which I totally forgot the star class to mention. Where is it? XGBM. I saw it. XGBM is one of the best. Boosted trees, yep, which are GBMs, gradient boosted models. That's a good complex model. And we mentioned this at the start of last class. I mean, at the start of end of Friday. So GBMs are very powerful models. If you were to choose a very simple model, what would you pick? Like, what's your good simple model? If you want to give someone a very simple model, what would you use? GBMs are very good complex models, but it's like pulling out like a $1,000 fillet knife to cut butter. I mean, that's awesome. It's gonna work great. You're gonna be like, whoa, the linear or the GLM. So the just the standard old vanilla, which those have no regularization. Which I'm not saying that's wrong, but GLM or GLM net are generally pretty good. So your GLM or your GLM net are kind of a good starting off point, especially if someone wants a pretty simple model. And if you're controlling for regularization, especially for a predictive model, GLM net would be great. And then when you go to more complex models, if you want to do something that's a little more like you don't really get to see what's going on in the background, then you might go to like a gradient boosted model, and you might go to extreme gradient boosting or random forests. And then once again, what you do when you make models is you make a bunch of models. So as you notice, your take home is literally doing that. Your take home is kind of the point we want you to get to be able to make models and to be able to look at models and see how well they're doing. And what do you notice about a lot of the code, especially with the carrot package? What do you notice about a lot of the code? Is it pretty hard to write? Are you like, oh gosh, this code, man, I'm just writing tons of code and I have no idea what is this doing? Or you're like, oh, I just changed this one thing and it works. Oh no, I have to set up a new tuning grid. Oh, I just need to change what my fit control is. Like almost the exact same. Yeah. The coding gets pretty easier at the end. Copy paste, it's copy paste. Especially with the data mining 3 carrot thing, the code should be change the one thing, pretty similar. It's like, oh, I just need to change the method. And if you change the method, you probably need to set a new tuning grid. And then you have to watch out if your Y is categorical, you have to then change your fit control to fit on either accuracy or AUC. So knowing like what the code is doing is important. And that's one of the things we focus on in this class. It's not like just like we write code. It's like, what's the point of this? Why are we doing this? Why are we writing this fit control? Why are we doing this? And then you can make the changes you want and you can write more advanced things. And that's why we teach you how to write functions, because the things some people have shown me, I'm just blown away by. And the last thing I want to mention, which we did talk about on Friday before this speedrun right here, the last thing I want to mention is about the complexity parameter. And I feel like we've talked about during office hours, and that's why I'm like, I know we've talked about during office hours, but you're not required to watch office hours. So I don't want someone to be like, you never mentioned this. We're going to mention it here. The complexity parameter right here, and it's in your assignment. This complexity parameter is how much we need in a return in either the SSE or the impurity reduction to split the tree. So the complexity parameter is how much of a return we need. So look at this. This is saying we need only a very what return right here. Look at that right there. We'll zoom in on if we can. This is saying we need a very what return to split the tree up here. Just think of it, don't think of it as a number, just think of it as a quantity, a very what return to split the tree. A very what return. To split the tree, we need the SSE reduction or the impurity reduction to be very what. It's saying as long as it's very, very what, we can split the tree. We only need to achieve this reduction to split the tree. To split the tree, we'd only need a very low reduction. So do you think that tree is going to split a lot or split a little? If we're saying, oh, we'll split the tree as long as we get like a penny. If we can split the tree as long as we earn a penny, would we split the tree a lot? And I remember the example I used in office hours now. It's like if I'm saying to you, as long as you make one free throw an hour, you will continue to shoot free throws. You'd continue on for a long time. So these are going to be your bigger trees. When the complexity parameter, which we will tune on, is very small, you'll get bigger trees because you're saying we will continue to split the tree as long as we get this reduction in either the SSE, which SSE is bad, that's sums of squared errors. We do not want errors, and we do not want impurity within the leaves. Impurity is bad. It's where things are not in the right category. So if we reduce the impurity by this amount, if we reduce the SSE by this amount, then we will continue to grow the tree, and we will get very large trees here. Then we go down here to where we're saying, wait a minute, we need this much of a return on the reduction in SSE or the reduction in impurity. So the complexity parameter says this is how much of a return you need to control the complexity of the tree. Think about this. How complex is the tree? a tree with a high complexity parameter, would it be a big tree or a small tree? Like if the complexity parameter is very large, the tree will be very wide. If the complexity parameter is very large, the tree will be very small, because we're saying it's going to cost a lot to make this split. So it's like a cost thing. It's the same thing we're talking about previously. It's the cost of making the split. And we're saying, okay, you have to have this much to make the split. It costs you this much. You need to be able to make this much of a return. And the tree's like, oh, I can't do that. I can't return that much to you. And it's like, well, too bad. So now the tree is not going to split. And right here, I'm just making sure it's the same as SVM. I'm like, okay, high cost in SVM will make few errors, and that'll make that'll make an overfit model. This model will be underfit. It is reverse. I was thinking through it in my head. So it's the reverse of SVM cost. Because if you have a high complexity parameter, so don't think of it as cost. Do not write down that complexity parameter as a cost. If you have a high complexity parameter, you're saying you must achieve this much to make the split. And if it can't achieve that much, it won't make the split. So with a high complexity parameter, the tree will not split because it can't achieve it at times. So you will get models that are often underfit. And we really see that right here because this has a very low, that is going to be, it's quantitative. So that's going to be an R squared. No, it's an RMSE or an R squared. It's an accuracy. My brain, it's a categorical. Yeah, because if it was quantitative, it would be RMSE. 320. And so that is an accuracy right there. So this tree has lower accuracy. And when we go up to here, we can see trees with higher accuracy. Now, what is the best complexity parameter right here? The best complexity parameter on this screen is what? The best complexity parameter on the screen is complexity parameter number what? We should be able to easily identify, and then we'll do the speed run here in a second. We should be easily able to identify the best complexity parameter. It is complexity parameter number what? Close, close, close. The best complexity parameter is complexity parameter, and the answer is it doesn't matter so much. Is number, someone gets 1,000. Who's going to be first? Everyone gets 1,000 who's voting here. Vedrina, Madeline, Yaji. It'll be number 2. Right there. Number 2. So number 2 has the highest accuracy, but it's kind of a moot point because the accuracy standard deviation is so large. So if you look at this and you look at this, they're all virtually identical. It's kind of a moot point between those because anything with an accuracy of about 82.3 or so, or 82.4-ish, is going to have 10. Okay, I was really afraid. I thought 10 might be the highest. But anything with an accuracy within about 82.3, which is all the way down to here, every model from here up is virtually identical because they're all within one standard deviation. So after about 15, there we go. So after about 15, the models get worse because all these models right here are within one standard deviation of the best model. So if you can't see, there's the accuracy, there's one standard deviation. All those models are within one standard deviation. So 15, so the 15th is, that's 20, 19, 18, 17, 16, 15, because there's 20 models right here. So every model from here up is about similar. 2 is the best because it has the highest accuracy. So that is why this one is the best. This is the best because it has the highest accuracy. Does that make sense? Highest accuracy, best model, and then every model within one standard deviation of its accuracy is, yep. Good questions, good questions. We got enough time for a speed run to end class. Good questions. Always be asking those questions. Be like, how did you know that's the best? You got it. Let's do a speed run. We're going to hop over here to the main screen. Oh, go away. And because the main screen, we get the fun speed run stuff. Okay, we got the screen up. Zoom in just a tiny bit right here, and guess what? It is time for a speed run. Let's make this happen right here. Let's end off with a speed run. Look at all those Mega Mans. Those Mega Mans are just hyped for the speed run. We've done 193 Stat 2-1 speed runs. Of course, I've done a lot of tests with these. And the picture right here. Okay, let's do this. So we are talking about, I get to say what we're saying with the speed run. We are talking about support vector machines and how support vector machines work. So how do support vector machines work? Let's do this. When we do a support vector machine, the whole goal, especially with categorical or quantitative data, is to figure out a hyperplane. So we need to know a key term right here, and I think I'm actually going to write this. We need to know a key term. What is the hyperplane? The hyperplane creates separation or a linear relationship in the support vector machine algorithm, in support vector machine. So let's draw this support vector machine. Oh, I'm not going to win the speedrun. So in the first example here, where we're talking about categorical data, we have right here categorical, and we can see a hyperplane like we saw in the notes where we get this. And then we also should put in this exists one dimension higher than our data. There we go. So this exists one dimension higher than our data. I can't make that clear enough. And so we see this right here where we have our data, and let's draw in the points now. And we put in some spacepen points that are just following the line right here. And then we've got the red, and we go right here, and then we go right here. And then we also see, see, I can't draw the 3D one for the linear stuff because that one's just insanity. We see right here where we have a graphic like this, and we've got some nonlinear relationship, and then we bring it to the higher dimension, and I'm right off the, there we go. And when we bring it to the higher dimension in a 3D world, here's a 3D graphic. This is going to be the worst 3D graphic. It creates some sort of linear, this is a 3D graphic, and I cannot draw 3D, but it creates some sort of 3D relationship in the data. So we can't fit a linear relationship right here. That's bad. But when we do this, it creates this linear dimension in this higher world, just like, whoa, no way. So that's what we got going on right here. This is the whole point of it. And then how do we find this? But how do we find the higher dimension? Say it in the chat, people. How do we find this higher dimension? I don't know. Brian's brain, he's going to lose the speed run. How do we find this higher dimension? Something. I'm running out of space here. How do we find this higher dimension? I need to know. The kernel trick. Nisha, 1,000 points right there. The kernel trick. There we go right here. The kernel trick is how we find this higher dimension. We have some key choices for this. We have the linear, we have the polynomial, and we have the radial Gaussian. So we're going to go, we'll scroll down, do this all on one page. We got the radial Gaussian. Is that how you spell Gaussian? That's how you spell Gaussian. I don't know how to spell Gaussian. I don't spell Gauss's name. So that's from Gauss, who created the normal curve. That's the, yeah, dude. So we have right here the kernel trick. So all this kernel trick is, like, what is the kernel trick? What is this? It is a way of finding a new transformed variable created from ours that will be added. Will that go off the edge? Be added, cool, to our variables. This creates the separating hyperplane or linear hyperline. Hyperplane or linear relationship. Okay. So with this right here, but how do we know which parameters? How do we know which parameters we're going to use for it? Like, we've got this cost parameter, we've got like cost, we've got gamma known as sigma, we've got d for degree for the polynomial. So we should probably put these up here. So we've got cost at all times, and then we got polynomial has d for degree, and it's got the sigma right here for that one. Sigma. It's just the gamma. How do we know how to pick? How do we know which parameters to pick? I don't know. Anyone got an idea? We're 50% done. How do we know? This one's going out to Andrew G. Andrew G, you got to beat this. Can you go sub 10 on this, Andrew G? Andrew G, I don't know if he can explain support vector machine sub 10. That's tough. He's going for those 455s in Mario, but he can't go sub 10 in explaining support vector machine to senior students. Oh no, and I need your guys' help. We're not gonna win this out. The world record is 9:59. We have to go sub 10. How do we know what to do with these parameters? How do we know which parameters? What are we gonna do with these parameters? We've got cost also, but what are we gonna do with these parameters? How are we gonna know which parameters to do? Tune them. That is literally it. Exactly it. That's exactly it. We're going to tune these parameters, which means we're going to make, oh gosh, we're going to make a grid right here. I got people trying to wreck this speedrun on me. Not happening. We're going to win this speedrun. We tune these parameters. What does it mean to tune them? Tuning them is when we try different values and find the best values that work on the what portion of data? On the, oh gosh, no, I'm going to lose the speedrun. We tune them to figure out which values work best on the something portion of data. Like we make our model from the training data, and then we tune it so that we see it works on this portion of the data. And then we also then test it on a holdout. But that middle portion of data, that's something with K, it's a certain portion of data. We try to validation, there we go, on the validation portion of the data. So that's very important right there that we tune it to the validation and we see which one works on the validation. Tuning them is when we try different variables and find the best values that work on the validation portion of the data. And then that's pretty much it. From here, we see if our model works the same on the holdout. We try to find a model that works no worse than 10% worse. So then we would do like RMSE holdout divided by RMSE validation. That'll do it right here. And or you could do AUC holdout. You want to find about a less than a 10% difference right here. And then we should put a caveat here. Models that are within 1 standard deviation are considered similar. And this is just like RMSE. And we're doing a lot of classification. We'll do this as AUC instead. AUC holdout versus AUC validation. Just a ratio of those two telling us what is the differences in AUC right here. And you can reverse these if you want, but you don't want to see about a 10% difference in them. You don't want to see a change. But if it does better on the holdout, that's good right there. So you'd want your holdout to do about 90% as well as it did on the validation, because AUC, higher AUC is better. It's the way in which we correctly classify. We correctly give the yes class a higher probability than the no class, and we want higher AUCs. And last but not least, the models that are within 1 standard deviation are considered similar. So what we're going to do right here, we're going to take the AUC of model 1 and subtract from it the AUC of model 2, and then we will divide by the what of the two standard deviations. So say it in the chat for me. We're going to take the 2 AUCs of the model for comparing AUCs for categorical models. I think someone just said it. And don't pick them based, don't pick it based on that. You'll overfit to holdout. Nice job right there, Jordan. And larger of the 2 AUC standard deviations. Boom, initial right there. And that is sub 9. We just jumped from the first model, or the first person speed running this, was sub 10. That was some guy teaching at some random university. I can't remember. I don't know. He didn't. We still invalidated his run. But this is, man, we need to do more speed runs. Sorry I didn't do as many. We should have done a speed run for every topic when we finished. I can't say I covered everything because this is a speed run. So I can't say I've told you everything. I'm sure there's things we didn't talk about. Soft margin misclassifier here. The cost parameter. Where are we tuning? We also tune on cost, which is C. And then we did talk about more in depth today, other topics. So I can't say, see, I'm cheating. My speedrun just got taken away. They said you added to it. Nope. So that's got that right there. And that pretty much does it for class. If you want, you don't have to. I've got this right here. I added this a while ago. How do I show it? I can't hover over it. This right here, if you haven't subscribed to the channel, I think it works. You don't have to subscribe. But this thing right over here, if someone hasn't subscribed, it's lower. It's supposed to like, oh wait, did someone do it? Oh, wait, it looks like someone did it. Or maybe not. It's like a boss meter. Yeah. We'll have the Kahoot at 3 p.m. tomorrow, looks to be, because I'm finishing up the test. So start studying. The Kahoot will help you kind of finalize your knowledge. And then I can't tell, does it say 4 or 500? Yeah, someone might have subbed. But yeah, I put that on there, and hopefully when we do Kahoots and stuff, I don't know, I should put that. Can you work over a few questions on the homework I got to do tonight? Yeah, which questions do you want? Well, up in here, we'll start doing some homework right here. Which questions do you want to do? Just say any question you want, and we'll hop over there and we'll start doing that. Let me pull up the homework. And thank you guys. Great class today. Support vector machines, not who feels like support vector machine, you got it. Like it's like, okay, it's just like we're just having it figure out the higher dimension kernel for us to use. So hopefully you're like, kind of makes sense. It's just going to figure out the extra dimension. We're going to tune it so it figures that out. It's going to do the work for us and create this model that adds an extra dimension, hyperplane, or creates a linear relationship for quantitative. I don't feel like it's too complicated. It's just crazy that people think these things up, that think of ways of doing this. Let's hop over here. Tomorrow's class is review. It'll be review, and we won't have neural nets on the test. Maybe I'll talk about neural nets a little bit tomorrow, but I won't put them on the test. I thought support vector machine might take a day and a half, so I budgeted more time, and I've already said support vector machine's not on it. I get of it kind of, but I don't really understand how are we supposed to apply the kernel method. So the kernel method, it's not really the method. Basically, the kernel is like saying, do you want chocolate, strawberry, or vanilla ice cream? So the kernel right here is trying out different ways of making it work. So when we try to find this higher dimension in the data set, we have different ways of finding the higher dimension. So we can pick different kernels which find the higher dimension in different ways. We can take like the chocolate method, the vanilla method, or the strawberry method, and each method will come to different answers for the hyperdimension, the hyperplane, which is going to go through the hyperdimension. The current homework is not bonus. The only homework bonus is the support vector machine neural net. You are still required to know support vector machine for the test, but since I was like, I just don't want to, you're still required to know it, but I didn't want to put so many assignments out there. So it's the last one, support vector machine neural nets, is the bonus. I'm just gonna make sure I before I say things. Can't get the manual GBM to work. We'll take a look at that here in a second. We got some other ones. Is this, I think, so is it a function in R? Yes. Here, I'll show you real quick. Let me hop to the screens. Right here, you'll see right here the train. This is, and we can all see it, good. This is using support vector machine radial. So this is the function inside of R right here, the support vector machine radial. And you could change this to support vector machine linear right here, and that's the different ones you can use. So that right there is you picking your kernel. So you don't actually tune on the kernel. I wish you could. I wish they had a support vector machine that just tuned across all kernels, and then you could just see which one works the best. I mean, you could create a function that runs all three of them and then puts them all in a list. I mean, it's not a bad idea. Just create a function that runs all three and then puts all three in a list and then says, here was the best. Because, I mean, a lot of times I'll just run all three to take a look at it. So that's what people often do, is they just write their own functions that they could just put in their y. Just think about this. Every time you run this function, the only important things you're really running right here are y tilde x comma data equals. So you could create a function that, you know, runs all of these. It would set up your fit control, and you would literally just do like support vector machine check. You could call your function like, call it support vector machine check. And then you would go right here and you would just have it input. We'd have to do a formula, but you'd literally just put in here y tilde x comma data equals. And then from here, everything would be the same. Like it would set up this fit control. You'd set up your different grids, and then you would have it put everything into a list. And then it would have it report back to you, maybe the list. And you could just run them all. And all you would have to do when you run support vector machine check, I don't think that'll work as a format, but you could just do it right here. Yeah. We'll do that real quick right here, and then we'll hop to, I think Kelsey had some questions. We'll do that. So we should be able to do this. The body fat, we should be able to run it. Yep, it's working. Okay. So when we look at the results right here for the support vector machine, this is kind of a good way to end class, and this probably will take a moment. Support vector machines are not quick. They're not quick. They try, it's very computer intensive. So this is probably when my computer slows down. Oh, it finished. It's not quick. It finishes. So here's the cost parameter it chose, and we chose the radial. So here's the gamma or the sigma as it's known up here. So this is the sigma it chose, looking at the grid of sigma we could choose from. So just in case you want to see, this grid of sigma is as follows, and it chose this sigma right here as the best sigma to use. And then also we have these cost parameters. Now be very careful. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and I believe 5. How many different models are we picking from? And I think I know the answer. Pause for a moment and think about it. I think I just said it 13 and 5. So I think we should be picking from 65 models, if I am correct. Oh, my brain just blinked because that's not the answer. By point, oh my gosh, it's this. Oh, no. Okay, I see what it is. This is not -1, -2. This right here, this sequence right here, see, that's where we make an error. This sequence right here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and that's 13 times 13, which is 169. So I just counted the things incorrectly. So we're looking at 169 models because there's 13 values of sigma, and that's going to tune the radial, that's tuning the gamma, and then there are 13 values of the cost, which is how much it costs us to make these errors. And then we have here the best tuned model right here, and then that's going to a force grid. But really from here, we're just looking at these results. When you go to look at these results, and we should have some graphics for it also, we can probably make some graphics right here because we should have a way of graphing it. I don't really graph my support vector machines as much. Let's see here, and once again, you know what, I'm gonna try the variable importance. I'm gonna just see if I can get the variable importance out of this, because we've been trying, like, as I was saying. So Anisha right here, if you look at this, the RMSE of this model is 4.04. So that's the typical miss we make when predicting someone's body fat is 4.04. Now what we should be able to do is we should be able to change this. I think everything's set up right here that I could go and make this a GLM, and we should be able to go to GLM, and everything looks accurate. And in normal, we got a lot of errors. Uh-oh, something is wrong. All our RMSE metrics are missing. Body fat, GLM, what happened? So try to do something really quickly right here. Set seed, GLM, method GLM, data body fat. We don't want to do a GLM net right now. Method, is it not liking the verbose? It might not like that. There we go. Okay, that argument was not meant to be there. It's just that's not used for that one. And now we go right here, and we take our GLM. We drop in our GLM. We've still got our support vector machine, and here we are. And it's kind of sad because the RMSE of the support vector machine is well within one standard deviation. We can take right here and take this RMSE and take this RMSE and then divide by the standard deviation of the larger of the two, which that one's ridiculous. And they're very similar. These two models have about the same predictive power, and we can go right here and quickly change this, and hopefully this is helping people a little bit with the assignments, because if we go to GLM net grid, we don't have a GLM net grid right now, but we're just going to take and we're going to put in here some values of alpha and lambda. And so we're going to go here to alpha, and alpha is our mixing percentage. So the mixing percentage has to be between, let's go to a sequence from 0 to 1 by 0.1. And then we're going to go right here, and we need a lambda. Lambda is the cost parameter, if I'm spelling it right. Lambda, I knew I made an error right there. And the cost, this might actually work as a, no, it needs to be from negative, because it needs to be like from -4 to -1, because the cost, this will make it very small cost. We can view this right here to look at the cost parameters we've created, and these are cost parameters that will work, because it's going to be the weight. And actually, we go a little bit higher. If we go here to quick questions, so we could use other kernels as well besides the radial kernel. Yep, exactly. Yep, that's it. Totally, Anisha. That is 100% correct. You can use any kernel you want, and oops, any kernel you want to use. Let's go to this. Let's try it. I think this will work properly. I'm going to go -1 first. Okay, let's try this. Okay, there's the GLM net grid. And now we should just go to GLM net. Change this to GLM net. And it's running, and it ran. And let's plot it, because I want to see what that did. So let's go to plot, GLM net. And here we are. And then let's get the results for the GLM net. And we're going to go here, change this to GLM net. And here is our RMSE. And it looks like it's hard to get an RMSE lower than 4.09. And we still have the large amounts of uncertainty. But I am noticing, please notice this is huge, that this right here, the regularization parameter, which we only used those 3 right here. Well, that's an error. So regularization parameter right here. And did I not resave it? I think I might not have saved it. Okay, now it took a moment longer. We're still not getting them. Let me go to regularization parameter, my lambda. Let's go to lambda sequence of 0.001, 0.01, 0.1. What is going on? I think I've misspelled lambda. Because it's not, I think it's using default values. Oh my gosh. Why am I forgetting how to spell tune? TR control. Tune grid. Yeah, it's got a capital G. I was like, I'm going to make an error on that. So I didn't have my tune grid in there. One thing, tune grid. It always gets me that these don't. There we go. I was like, why is it not doing this right here? And now, there we go. There we go. And did I not beat it out? There we go. And we got right in here. So I do want that. Let me change this now. Okay. Sequence. So we want the very small numbers. From -6 to -1, going by 0.25 and 10 raised to this sequence. Okay, that's taking a moment. And there it is. And we want the lowest RMSEs, so it's somewhere in there. And we're still getting 4.09. So we really aren't achieving much of a... It's somewhere in here is probably the best model. And if I were to zero in on this area, but we're really not seeing a really good model that is different from the other ones. And why am I saying that? Take a look at... The reason I'm disappointed is because when you look at these 3 models, look at the RMSEs of these models. So we should be able to just go here and let's look at the RMSEs, and then I'm going to hop to the first question Kelsey asked. I think we can just pull the RMSE off of this. We should be able to. Yes, we can. So here, let's just append together all 3 RMSEs to show it. I mean, the code's going to look ridiculous, but it'll work. And so we're just appending together all the RMSEs, and you can see it right there. All the RMSEs are almost what of each other. On the second one, what's the second one? The second one, oh, support vector machine. Well, yeah, I know, right, Anisha? They're all basically identical. I mean, for all intensive purposes, the model typically misses someone's body fat by 4%, which I guess isn't that bad. The model typically misses no matter what. And I kind of want to run, I think we have a GBM down here. Do we have a GBM on it? There's a GLM net. And if we have a GBM, I'm just going to run it real quick. Or do we do extreme gradient boosting? Which just has more parameters to tune. And yeah. Okay, let's hop to Kelsey's question here. Let's hop to Kelsey's. Kelsey was saying 3, 5E, and 8. 3, 5E, and 8. Okay. 3, 5E, and 8. Can you start me off with 3, Kelsey? Kelsey, what does 3 say for the start of it? What does your question 3 say? Which one are you talking about? And 5E and 8. Start me off with the very beginning of them. I want to make sure we're doing the right ones right here. 3, 5E, and 8. 5E. Where's E at? And 8. Where's question 8? Sorry, the numbering got all crazy. Oh, here we go, right here. Wait. Now fit a regularized regression model. Setup. Okay, cool. Now fit. Cool. Okay, good. Hey, it's question 3. I just hate that there's no, like, it's so many. Okay. Now fit a regularized regression model, set up the GLMnet to be the result of running expand grid with the considered all the alpha values of this right here. So when you look at this right here, it's telling us the alpha values and the lambda values, which is what we were just doing a moment ago. So we need to set up the alpha and the lambda values as follows. Let's make the screen a little bit bigger right here, and let's make it so we can set up our alpha and lambda. We need to go to GLMnet grid. You can call it whatever you want. And it's saying call it this. I mean, we can do that if we want. And the sanity check won't work. Okay, cool. Let's figure that out. And we're going to do expand grid, and then we're going to do an alpha. Alpha is going to be the sequence of 0 from 0 to 1 by 0.1. Now, whenever you make something like this, you can just double check what you're making. This is key. If you check it, you should see the sequence it says. So highlighting code and checking it is key. We want a second thing in the expand grid. I always hit enter right there, just kind of keep it separate so I can see where my separate things are. We want to do a lambda. Do not forget the D. I've forgotten it multiple times, and then the code won't run. And we're going from -5, and it's going to be the raised to 1. And that's actually what I think I just did a moment ago. It's just classic. It's what we often do. You can see it over here on my regularization. So going from -5 to -1 by 0.25 and by 0.25. And the big thing is it needs to be 10 raised to this. So 10 raised to. So it's not going to look, if we look at the sequence itself, it looks like, whoops, not EQ, but SEQ. So if you look at the sequence itself right there, it looks like that. But when we look at the 10 raised to, it becomes very small numbers because 10 raised to a negative number turns into decimals. So these are all like 0.00001, 0.0000177, 0.0000316. And so these are small decimals, with this being 0.1. That's just 0.1 right there. And you could confirm this, but we're good. We got this. Okay. We need to make our training and our holdout. So this is predicting what variable? What variable are we predicting again right here on this one? We are predicting, I'll see, because I need to make the training and holdout again. So we have to do the set seed right here. And our code's going to be very similar. We're just going to put our set seed right here. And then we're going to make the GLMnet. And so now, I think I have other code from this earlier. Is it electricity? Cool. I think it's, are we doing the electricity usage? Cool. Yep. And let me load in stuff, because stuff's not loaded in. Okay, I think we're good. Okay, got to change working directory. I should just set my working directory to my downloads. That would help me. Okay, good. Okay, now we're good. Okay, so we're removing out that. Okay, we need to do a training and holdout, which I think I already have some train holdout stuff on here. Did I not save my file from yesterday? Here we go. So since I've already made a training and holdout, we're going to go... Oh, do you think you figured it out, Kelsey? Good job if so. So since I've already made a training and holdout, I'm just kind of taking that code and let's hop it in right here. Oh, awesome. Here, I'll continue through this and we'll go to like the next one here. Put the start of the next one you want in there, and tell me the start of the next one you want to do. And this says split the data 5,000 into 5,000 training rows with a holdout using this. On the same line, do the sample, and then we want to do 85%. Okay, so that's where we're doing the percentage of it. And then we have to change this to the number of rows here. And I think we should be good. Let's see. Oh, I didn't do set seed. Purchase not found. We're not doing purchase anymore. And then we need to set seed. Because we don't set seed, we won't get the same results. And then I might need to check my randomness procedure. And let's check it. Okay, that's... Wait, oh, I did dim... Oh, wait. Did I call it reverse? Dim train... Did I reverse it? It's reversed. Wait a minute. Something weird happened here. It says we should get 5,000. Well, once 5,000 instead of something. I got it. Yeah, okay, cool. So this is gonna, yeah, okay. And that should be that. That's how many we're sampling. And we could take, these are gonna be the train rows. So we could say holdout rows. And this should be the holdout rows. And this will be the not holdout rows. So you got it. We'll do that one next here. Okay, that did it. Let me see here. Oh, the train. It's saying, oh, wait, so it's saying take the train as that. Big holdout. There we go. And then we are getting different. So let me try this. This is one of the big things that we pointed out. So RNG kind. So sorry if this hits people. I think it might reset it every time I do it. And let's see what we get. We now have it. Okay. So this is a big thing that hits a lot of people, and I think it resets R every time. Do realize that so many crazy things. I lived 98. We lost a comedy legend today, but he lived 98. That's good. Do realize that if you are getting different things, if you're getting different answers, please check. And then thank you for everyone who comes to office hours to see the sanity checks. But I believe they're all set to the RNG rounding, and I think R might reset this to RNG rejection. So I believe it's resetting it when I run it, or like when I reload R. So we are getting different results with the rejection. Oh, that's a totally different result. So maybe it was working before, and it does work now. We are getting the proper result of high of 21797, and you can see that right there, the 21797. So we are getting the sanity check. Yeah, and then just to fit the model, I think people might know how to do that, and we were doing the rest of the things there. Manually fit a vanilla partition model using RPart. Vanilla, so manually fit a vanilla partition model using RPart, predicting usage from all predictors on train with a CP of 0.003. So when we use RPart, which is in the notes a little bit right here, we will actually give it the CP of which it'll fit to. So let's actually fit the tree right here. So we can just call this tree, and we need to use the function RPart. So where's our RPart? There's RPart right here. So with this right here, we will actually put in the CP, and let's just hop over here and show it in the notes. Let's show it. So showing the tree off. Let's show the tree. Do we not? File, open. Let's go here to the tree rplot. That's not the one. Tree-based models. There we go. There we go. I knew we had the notes open earlier today. And so let's go to RPart. And here's the RPart. And here's the RPart right here. So we'll go ahead and grab these right here for the vanilla fit. And let's drop it in. And let's do it. So if you look at this right here, the RPart is just going to have y tilde x comma data equals. And so using the RPart function, we're just going to go ahead and predict the variable we want to predict. Are we predicting the same? We're predicting usage, right? So, and then it wants us to run this code here next. So let's go ahead here. We're going to store final tree. We can call it tree. Just classically call it tree. And so let's go to usage. And then we're going to fit with a CP of this right here. We need to delete the extra period. It should like it. It did. And visualize the tree. Here's the tree right here. And then we can look at some of the relationships within here. So this will show us kind of the idea of what is going on right here between the relationships. Is it going to show? And this just kind of gives us an idea that as we see, let's take a look right here. Graphics loading. So the predicted usage, and we're looking right here about what we predict and what we observe as we increase the values of which variable again. We're looking at on electricity right here, and the interest is the mean. So we're looking at the mean. Let me vanish right here away. We're looking at the mean and the predicted usage throughout the model as we see this increasing right here. So we're looking at the mean on electricity increasing right here. So just understanding that there is kind of this monotonic relationship. As the mean increases, we generally see lower predicted usage. And you do see the observed, like these are all the individual points right here. So these are all the individuals. And here, I'll drop this code in the chat right here. But this is how we make the model right here, just putting in the variables. And we can also visualize the tree. Now we did make yesterday. So we added in some stuff yesterday. And let's show this real quick because we can actually view this a little bit better. And is it going to look nice? There we go. And so this is a little bit nicer of a plot showing us the relationships between the variables. and we can make predictions with it. Let's export it, save to PDF, and let's go to 12, 9, and let's go rplot06, sure. Oh, there we go. So a little bit easier to see what's going on here with this graphic, but you can see we're looking at the mean, which is the variable we were looking at previously and how that explained usage. But with a mean greater than this, they'd go to the left. And then with cooling hours less than this, they'd go to the left again. And we can look at where the higher usage is down here at the bottom. So with this right here, you can see the amount of usage people had, where these are the very high usage individuals. And then if you go down here, we're seeing lower usage individuals like 30. And I really love this because it color codes it. And this is fancy rplot. And you can kind of see where you have the differences between the groups. And it keeps it all in one line. A little bit easier to read. And I got the picture looking really good today. I was having issues with it yesterday. What does it say? Stat 201. I have no idea. So this right here is just the function fancy rplot. And it's in the rattle package. So that's a really nice... there we go, rattle. There's where I'm installing it yesterday. And so you get to hear these little extra things right here, especially during office hours. So if you want to run library library rattle, then you can run the fancy rplot inside of it. And you just do a fancy rplot of your tree right there, and it looks a lot better. And then was there another one, Kelsey? Does this make sense for this one right here? I think I want you to make predictions on this individual. So on a day with this, so it says, visualize the model, then follow the branches to find the predicted value of someone's usage who is not on the pay plan. So if you look, you've kind of got this right here, i.e. on a day with this, with a day with this, with a day with this. So you have to go through the tree, and you have to follow the tree down for this person. So the first thing we're going to ask them is, it's a lot because you kind of got to go back and forth. We're going to ask them, is your mean greater than or equal to this? So their mean is equal to, where's their mean at? Their mean is 70. So will this person go to the left or right? Their mean is 70. Will they go to the left or the right at the start? Their mean is 70. And yeah, and drop that one in the chat again. Just give the start of it, and then I'll find it, and then we'll do it. Yep, they'll go to the left. Yep, because their mean is greater than 70. So they'll go to the left right here. And then we have to ask, is their cooling hours less than 210? Is their cooling hours less than 210? Okay, their cooling hours are less than 210. So they're going to go to the left right here. Next question is... we're on this because they went left. Is their heating hours less than 384? Their heating hours is not less than 384. Here's their heating hours. So we would say no to this one right here. Are their heating hours less than this? No. Oh, cool. We're done. That's it. That's the answer. Should be 45. We'd predict that their usage would be 45. And double check my work if you want, but I'm pretty sure, and hopefully other people are getting that, I'm pretty sure it'd be 45 because we just ask the questions till we get to the point, and you won't use all the information. You'll just go through as the tree goes down, and you'll make the predictions based on just whatever one it's asking you about. And then what does number 8 say? And then feel free. I think Jordan had more questions too. What does number 8 say? What's this? Spell check. Spell check. Out of curiosity, let's find the errors of the holdout sample. The GBM method technically had the lowest. Out of curiosity, let's find the errors on the holdout sample. I just hate that I can't like zoom through the question and find it like that. I need to put markers in for all these. Out of curiosity, let's find the error on the holdout samples. The GBM method technically had the lowest estimated generalization error. So imagine we picked it as our final model. Does it end up having the lowest estimated error on the holdout sample? Note, remember to use set seed on that line predicts the nearest. Prediction of the nearest neighbor model. If one model did a lot better than the GBM on the holdout, should we switch? Why or why not? Okay, cool. If one model did a lot better than the GBM, should we switch? And how are we going to compare our models to see which one does better? We're going to take, and what variable are we predicting right here? Because either we're comparing AUC or we're comparing RMSEs. So I have to know what variable we're predicting. But still, we'll use two variables that are within what. So copy paste the hashtag of the results, running these commands since, yeah. And so what we want to do, 17B and 2G, my sanity check's a little off. And it is still doing that. Jordan, you might have to send me that one. You might have to send me that and I'll take a look. And I might have to be like, okay, because it should, if it's the one we were doing yesterday, and yeah, I don't know. Tell me if you think the grader's unfair. So I think the grader's been really fair this summer. She's worked super hard. When we compare models, we're always trying to see if models are within what of each other. When we compare models, we're always trying to see if models are within what of each other. When we compare, bingo. So it goes back to what we were kind of doing in the in-between moments. Where did I put that set of stuff? It goes back to the in-between stuff we were doing, where I had all that work I was working on, where I was making my different models and then looking at them. Because all we're trying to do, sometimes when you have too many tabs open. Yes, this was it. Which then I made my results all crazy. So the whole point of this, and I kind of did it right here. I don't know if this would be the best way to report it, but this right here is showing the, we still have the RMSE on this. And when you make your different models, we'll clear the output. When you make your different models, the goal of making the different models is to look at the RMSEs and to see if they are within one standard deviation. And so this is the kind of roundup of it all to say, okay, we've made these different models. And then in truth, with this one right here, this RMSE is 4.09, this one's 4.05, this one's 4.10. The larger of the standard deviations is around 0.34. So all these models are virtually identical. Every one of these models has about the same predictive power. There is no strong arguable reason to use any of these over the others because they all make a typical error of about 4 or 4.1. So they all have an error of about between 4 and 4.1. There is no, in this example I'm showing right here, there is no compelling reason to use one model over another besides personal preference, which someone might have. Someone might be like, I really like let's just use regular old regression. Sure, cool. It works just as well as the others. Does that make sense, Kelsey? Like what we're trying to do with this right here? Mentioning the numbers is key. I'm trying to update, I'm trying to update the assignments, especially. It's just one thing I couldn't do between the summer and this semester because it's like one of these days I'll sleep. Wednesday night is just like tomorrow night. I'm just like, tomorrow night I sleep. I go to sleep and I sleep. And I'll be like, oh my gosh. Because I'm trying to prepare for Sunday, and I really appreciate everyone. Everyone's been working super hard, and everyone knows the world is just, it's the C19 thing is just insanity. So I really appreciate everyone because I know a lot of different stresses, and everyone else has different stresses. And I'm really excited about my move to Texas, and it's a 14-hour drive. So once I get my place all packed up, been working on that for forever. Once I get the place all packed up and ready to go, 14-hour drive to Texas, and then I get to be with my fiance. So it's a big pot of gold at the end of the rainbow. So I got her picture right here. So that's got it right there. Any last few questions right here? Any last few questions? I think we are good. I'll probably be on later tonight. I'm going to get some stuff done around here, but great job. I think people are doing pretty well. Be working on the take-home. We have the Kahoot tomorrow. We have class tomorrow. We'll be finishing up, and I'll be packing up. But that's about got it. So I will see everybody later. Let's end with a little Star Wars. Jason, can we continue on, Jason? Jason, we just got a little bit longer here. Jason.
5 hours. We've almost got these new intros ready. We're almost there. This has been going for like 20 hours.
I'm back, Jordan. What does 1.5C say? Jordan, you there? You there, Jordan? There's a delay, so if I'm like saying I'm leaving or something. Jason said we could go longer. I convinced him this time. I convinced him to go longer. What does 1.5C say? Oh, look, wait, that's 1.5 points. We don't want that. Hey, we found it. We found 1.5C. Okay. See, look, is it this one right here? Now estimate the generalization error of a vanilla partition considering that the CP of raised to the sequence, blah, 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 blah. Save the output of train. Okay, so we're going to go ahead and grab some code right here because we love to copy code. That's what we do. And we're going to have to tune the CP. So probably a good thing to Google right now would be CP equals. No exact match. Oh, CP equals. Here we go right here. We've got the R part grid. We're going to grab this code right here. Grab the code. Oh, yep, we can do that. Oh, I'm on a wrong one. So people were wondering about this task right here. This is what this task relates to. Now, this is not the answer for this task. And of course, we have to do the satisfying thing of cleaning the code to make the code look nice. And we just see our usual pattern with the package right here. No, that does not look nice. That looks nice. And that does not look nice. That looks nice. And we only see the CP right here. So this is only tuning CP. So this code right here tunes the CP. It's just the tuning of the RPART grid. But let's hop over to the very important part. Well, actually, we actually need this. You should find that the list of important predictors looks quite a bit different. Oh, so I think we do need this. What variable are we trying to explain here, Jordan? What is the y variable we're trying to explain in this problem? Do I have the data set up? What variable are we trying to explain? Is electricity usage? Okay, cool. It's like, okay, so wait, I haven't closed R yet. Okay, let's see. Okay, so we're trying to predict usage. We've got the train data set up properly, I think. We're doing from -5 to 1, raised 2. We should be good. Oh, look. Hey, oh, length. Length is not correct. We want by 0.2. So how do I know this? Take a look at this right here, and then we make this sequence here, and we raise 10 to it. So that's correct. We've got our RPART grid. I think we're good. Y tilde x, comma data equals. We are now making our trees. And so what this will do, we can also go and look at the RPART, and we want to look at the results for it. This will print off all of our results. And what is our best tune right here? What is our best tune CP? 10,000 points first person. What's the best tune CP on this? What is the best tune CP on this? We can run the code and it can tell us. Ooh, my eyes are blurring between some numbers. Okay, I think I see it. What is the best tune CP on this? We should be able to figure out, and here's a hint. That's the important one. So I figure I'm like, maybe someone, you might not know that that's the important. So what is the best tuned CP on this? I know this is not the question exactly right now, but yep, 13. Bingo. 13, that's the one I see. We might be wrong, but we don't need to look at it. We can go here to the results, and we can go to RPART and $ best tune, and you see this gives the CP of it right here, but we want the row names, and we put here row names. That's the row name, and then we go here and we put it in as the row we want, and there's the row name. So just kind of watching the methodology in that I'm saying, like, okay, what is the row name of the best tune? Okay, now return to me that row. So all this code does right here, which I put inside of here, is returns 13. And so I'm just going to the results, this whole big thing of results, and I'm only returning row 13. I'm just saying, just give me the best tune result out of it. You could do something ridiculous like this and say, give me, oh, I guess if, because it's, this is ridiculous. Don't do this. I'm just having my fun for a moment. As.numeric, and then we should be able to subtract it. Yeah, and that gives you everything but row 13. Don't do that. And you don't need the as numeric, but hey, it works. Because it was using it as a word, and it can search for that word. So that's the best tune right there. The best tune is a CP, which controls the complexity of the model. We'll show you how the choice of CP affects the, so let's look at that. So we're going to see, we're looking at RMSE. Is regression tree model the same as vanilla partition? Yes. A vanilla partition is a general term for either regression tree or classification tree. A vanilla partition, because partition, to put it this way, all of these are partition models, and vanilla partition just means like the trees. But the trees could be a regression tree, which means quantitative, or they could be a classification tree, and this one's a regression tree, but it's still a vanilla partition model. So vanilla partition model is the global term like humans, and then you can do like, like Americans, or you could do like this. You could do subgroups, but everyone's still a human. So everything still is a partition model, and vanilla just means it doesn't have the added aspects of bagging or boosted or things like that. Like we can do advanced things, like we can do bagging, which is when we take random subsets of our rows and create bootstrapped samples. So bagging is bootstrapping. Good question right there, Sarah. 1,000 points. Thank you for hopping and asking that question right there. That's what we like. Include the plot. Okay, cool. Let's take a look at this. So you would use, yeah, exactly. If you're doing vanilla partition, because GBM is gradient boosted models, and those are anything but vanilla. Those are like chocolate fudge with sprinkles and cookie dough in them, because GBM's awesome. Chocolate fudge with cookie dough. Yeah, I'll eat. That's good ice cream. And so we're looking at the RMSE right here, and we want the RMSE to be lower. Remember where Jordan said 13 was the best? This is actually model 13 because 13, 14, 15, 16, 17, 18, 19, 20, 21. Oh, wait a minute. Is it not model 13? 13, 14, 15, 16, 17, 18, 19, 20. Do we have 21 models we're looking at? Maybe I miscounted. There might be 21 models. That's 21 models. There's 21 values here. Because if this is 13, 14, 15, 16, 17, 18, 19, 20, 21. Yeah. I was like, well, there's got to be 21 because if that's 13, then there has to be 21 models. And so we get the R part right there, and which will show us. Cool. Plot, include this right here, which we just did. And then include the variable importance. This is the one Jordan was looking at right here. This is the variable importance. And let's take a look at it. Da, 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 da. Cool. Well, we can plot this also. Plot. Okay. So what we're noticing right here with the tree is it's not using any information from daylight hours. It's not using any information from hours below. It's not using any information from hours above. You've really got like 5 key variables right here and 4 minor variables. So I would say, there's 5 major variables and 4 minor variables, which we should be able to. 5 and 4. That's 9. I'm hesitant to do this. Yeah. You could change it, and I would maybe do a second visualization, or you could do this. Par mflow. Par mflow equals 1 row, 2 columns. Yes, I'm remembering. Here, Jordan, check this out. Check this out. Okay, so here's what I would include. If I'm thinking about how to visualize this and explain this to someone. Okay, that's got that. No. 1 row, 2 columns. Did that not do it? Am I going mad? Always the answer is yes. Where did I make my error in the par and fro? Is it flow? No. Okay, 2 seconds. Wait. I want to change this and just... Well, that worked. All right. Par, mfro. Mfro. Combining plots. They're showing it right here. Same code. 1 row, 2 columns. Oh, do I have to do it? No way. Nope. Can variable importance not be done like that? Or do you have to do it as 2 separate lines? Nope. I have done this before. We're going to take their card. Maybe this plot cannot be done this way. Okay. See, it's doing that. It can't. It can't. Wow. Learned something new right there. That's a bummer. Because what I wanted was I wanted to do this. That is... Wow. Why does it not do that? I think I answered right there. I answered that. So this is once again Brian going mad because the code doesn't do what he wants it to do. Because I know the function right here to change the plot options, but apparently when you plot the variable importance, you see we literally have this set up by a 1x2 and it goes full screen. So I have no idea why it does that. This is a crazy idea right here. If you have additional questions, feel free to ask. We're just kind of having some fun here for a moment. This will not work. If this works, my mind will be like, no way. It's not a ggplot object, so it won't work. Could not find something ggplotly. Is that not? Did I not run ggplot too? Okay. ggplot. Oh, it's plotly. Plotly has to be loaded. It's not. Okay. This has like a 0 chance of working. Okay, there we go. Yeah, it's there. Yeah, it can't. I wonder what that error means, but no, it's not a plotly object. But however this variable importance is being made, however it passes it through, it can't turn it into... That's so weird. Does it provide a fair assessment because it involves fewer variables? So the way it is, and let's look at the question specifically. I was just kind of having some fun there for a moment. So looks quite a bit different compared to the list. The predictors explain why this list likely provides a much fairer assessment than the ones produced by the linear regression. So the linear regression, which we can make pretty quickly, and let's look at that linear regression. To make the linear regression, we only need to do a quick few changes to this model right here, and let's see what the linear regression does. And I think I can explain why this is doing it, because I think linear regression is going to have way more variables in it. Let's take a look. So to make a linear regression, we're just going to call GLM. We're going to change the method to GLM. We're going to remove out this R part grid, and because we're not using the grid, and I think we're good to go. Yep, we're good to go. What did we do? Warning messages. Okay, we might be all right. I don't know if everyone else got those warnings. My ridiculous code right there. Okay, cool. The RMSE of that one is 26.95. This one, ooh, the linear did better than the tree. Interesting. And then we're going to go down here to the variable importance, and we're just going to change this, and then we're going to look at them. I wish we could do them side by side. And if you look at this, the linear regression versus this right here. So is this what you're getting, Jordan? Are you getting this for your tree, and you're getting this for the linear regression? Is that what you're getting, Jordan? Are you seeing these two things right here? Here's your linear regression, and here's your tree. And that's so interesting. If you look at it, the linear regression is only the weight of the variables is mainly from pay plan yes. So you have one variable basically dominating your variable, where here you have 5 variables as like your major variables and 4 variables as your minor. Like that's a minor, that's like a medium, and these are minors. Like here's your major variables giving importance to the model, here's your moderate variable, and here's your minor variables. But really in linear regression, you might have like the major variable, the minor, and the very minor. So you're seeing that one variable is basically dominating the model. Basically, one variable does most of the explaining in the linear regression. It's not really like, why do we have a bunch of variables in the model if one variable is doing most of the work of creating the model? We want the variables all to kind of contribute evenly to some degree. Not that they must, but the linear does better. You know what we could do right now? Because I'm just interested, and this is how we just do it. I mean, this is what the assignment's walking you through, is we go here and we go to GLM net, and now we need a tuning grid for it. So we're just going to take our tuning grid here, and we're going to go to GLM net grid and call whatever we want, and then we have to know what we have to tune on. We have to tune on, we're going to make this the lambda, because that lambda. There we go. I always misspell it, but not today. Ooh, that's not going to look good. And then, there we go. And then we go here to alpha. I'm going to go back. Alpha equals sequence from 0 to 1 by 0.1. Cool. Might not be what the question asks, but this is my GLM net tuning grid right here. And so then we need tune grid added to this. We need GLM net, and tune grid equals GLM net grid. And we've made a GLM net. We've got this error unexpected. Yep. What I forget, a comma, because I always do. And there's that. And then we're just going to take the results right here while this is running, and it already ran. And then we're going to take the GLM net, copy this in, and we're going to go right here, and we're going to look at the results. It's about the same. I mean, I think, yeah, it's a bummer because we're getting an RMSE of this. It's virtually identical, and the RMSE standard deviation is 1, and that's for and the RMSE here is 1. Yeah, they're all working about similar, which is kind of a bummer. None of these models are really standout winners among these, and we could plot the GLM net grid, which is going to be, what did I call this one? This is the lowercase, because I had another one in there. And we got something going on in here we could investigate, but really we're not, if you look at all these, they're all super close. I mean, it's just really hard to get a usage with a smaller error than 29.5. What I'm looking at, let me show you real quick, is you're not really going to beat this out. You didn't have to, sorry. You don't have to use the as numeric. I was just being crazy. because this right here is it's a character. So since this is a character, I turned it into a, oh, it's the first result? That's interesting. So you don't have to do that. I was just kind of being extra because I wanted that not to be a character, which it can look it up as a character. It'll still identify that. I wanted that to not be a character. I wanted it to just be the number 1. And I was just like, I don't know, because it was a word, and I was like, it still finds it as a word. Yeah. But good questions right there. So that wasn't needed. This code will work the same way, either way. So I don't worry about adding those on. These are just Brian being extra. I don't know, because what it was I was trying to subtract off that row, and to subtract it off, it has to be a number. So you can't subtract off a character. It can search for the character, but it can't subtract off the character using that stuff right there. I think that's got it. So did everyone get some good help right here? Does this make a little more sense on how to do the model building and what's going on with the code? And hopefully the theory makes sense. Getting ready for the test. Finish up writing the test today. And we should be good. Jason's calling me now. Jason. Can we keep going, Jason? Jason, go going. Jason?
5 hours. We've almost got these new intros ready. We're almost there. This has been going for like 20 hours. This ends now.